What if everything you thought you knew about the beginning of the universe was incomplete? We're taught that time has always been there, a steady arrow moving from past to future, framing our lives and the cosmos itself. But what if time isn't fundamental? What if the universe didn't start with a bang in time, but emerged from a realm where time had no meaning at all, a state so strange and profound that words like before and after simply don't apply? This isn't science fiction. This is one of the most thrilling frontiers of modern cosmology, and it's where our journey begins today. We're about to explore the idea of a pre-temporal universe, a cosmos born not in time, but from pure potentiality, a shimmering landscape of mathematical possibility where the rules of cause and effect break down and something far deeper takes their place. Imagine a reality without sequence, without history, without change as we know it, a silent, dynamic foundation from which everything we see, feel, and experience somehow arose. It's a concept that challenges not just physics, but philosophy, perception, and the very nature of existence, and it's supported by brilliant minds working at the intersection of quantum gravity, metaphysics, and cosmology. Throughout this video, we'll travel through breathtaking theories from the timeless wave function of the universe to cosmic holograms, from bouncing cosmologies to multiverses bubbling out of an eternal meta-reality. You'll discover how leading scientists are rethinking the Big Bang, why time itself may be an illusion emerging from something deeper, and what all of this means for our understanding of reality and ourselves. This is more than a science lesson. It's an invitation to expand your mind, to see the cosmos with new eyes, and to join one of humanity's greatest adventures, the quest to understand where we came from and what truly lies at the heart of existence. So let's begin not at the beginning, because there may not have been one, but here, now, ready to explore the mystery of a universe that started when time had no role. So we're left with this beautiful, baffling paradox right at the very start. How can we possibly talk about a before if time itself didn't exist? The word itself betrays us, because before is a temporal term, a word that only makes sense inside the very framework we're trying to step outside of. It's like trying to describe the color of a mirror using only the reflections it shows. This is the central puzzle we need to untangle if we're to grasp the concept of a pre-temporal universe. We have to consciously set aside our everyday experience of a linear, flowing timeline and try to envision a state of reality where sequence, cause and effect, and even the distinction between past and future simply do not apply. Instead of a void of nothingness, picture this pre-temporal state as a domain of pure potential. Imagine a vast, unchanging canvas of mathematical relationships and geometric forms, a landscape where the laws of physics as we know them haven't yet crystallized. In this realm, quantum fluctuations aren't happening in time. They are more like static, timeless patterns of probability, a shimmering tapestry of what could be. There is no waiting for something to occur because there is no duration to wait within. This isn't an empty stage before the play begins. It is the very source code of the play itself, containing every possible scene and character in a state of simultaneous coexistence. This radical rethinking of time isn't new. The philosopher Immanuel Kant argued centuries ago that time is not something we discover in the world, but rather a fundamental structure of our own minds, a lens through which we are compelled to perceive reality. He suggested that we can never know the true thing in itself outside of this temporal framework. Fast forward to modern physics, and thinkers like Julian Barber build on this idea, proposing that time is an emergent property, an illusion that arises from the complex interactions of timeless, fundamental components. In his view, what we perceive as the flow of time is actually just a succession of distinct, frozen nows, like pages in a book. The story gives us the feeling of motion and sequence, but the book itself just is, entire and complete. This framework forces a monumental shift in perspective. We move from a simple linear timeline with a definitive start point to a far more fluid and multidimensional origin story. The question changes from what happened before the Big Bang to from what deeper, timeless structure did our temporal universe emerge. It's the difference between asking what came before the first page of a novel and asking how the paper, ink, and author's imagination combine to create the story in the first place. This foundational idea, that time is not a fundamental stage but a character that appears within the play, prepares us for the even deeper and more astonishing scientific theories that attempt to describe this emergence. So if the pre-temporal state is this realm of pure, timeless potential, how does our familiar universe of stars, planets, and flowing time actually emerge from it? To answer that, we need to take a critical look at the story we've all been told about the beginning, the Big Bang. For decades, this has been the cornerstone of modern cosmology, the moment we point to and say, this is where it all started. The equations of general relativity take us back to an infinitely dense, infinitely hot point, a singularity where all the matter and energy of the cosmos is crushed into zero volume. At this t equals 0 mark, the math of Einstein's theory simply breaks down. The curvature of spacetime becomes infinite, the laws of physics as we know them cease to function, and time itself appears to wink into existence. This presents a profound conceptual hurdle. The idea of a singularity isn't just a physical challenge, it's a philosophical one. It effectively acts as a barrier, a cosmic keep-out sign that prevents us from looking further. Asking what came before the Big Bang singularity is, in the strict confines of this model, as meaningless as asking what's north of the North Pole. The model itself defines the beginning of time, so the question of a before has no place within it. It's the ultimate dead end, yet our curiosity refuses to accept that. The human mind instinctively rebels against the idea of a true absolute beginning, a creation from nothingness with no prior cause or context. This deep-seated intuition is a powerful clue that our model might be incomplete. The core of the problem lies with general relativity itself. It's a magnificently powerful theory, brilliantly describing the behavior of the universe on large scales, the orbit of planets, the bending of light around galaxies, the expansion of space itself. But it is fundamentally a classical theory. It doesn't incorporate the bizarre and counterintuitive rules of the quantum world that govern reality at the very smallest scales. And the initial moment of the universe was undoubtedly the smallest scale imaginable. Imagine trying to use the rules of continental drift to describe the chemical bonds within a single grain of sand. You're using the wrong rulebook for the job. Pushing general relativity all the way back to the singularity is like using a weather forecast to predict the trajectory of a single electron. It's a tool being applied far beyond its intended limits. This is where quantum gravity must enter the picture. Physicists have long sought a theory that can seamlessly marry the large-scale world of gravity with the small-scale world of quantum mechanics. In such a theory, the extreme conditions of the Big Bang singularity wouldn't be a catastrophic end to the math, but rather a transition zone, a bridge to a different state of reality. Instead of a definitive starting gun for time, the Big Bang might be better thought of as a phase change, similar to water freezing into ice or boiling into steam. We know the properties of water change dramatically during these transitions, but the H2O molecules themselves persist. In the same way, our expanding, temporal universe might be one phase, while what preceded it was a different phase altogether, operating under different rules, a pre-temporal, quantum geometric state where the very concepts of before and after hold no sway. This shift in perspective is monumental. It transforms the Big Bang from a mysterious, one-off event into a potentially understandable process within a larger, more complete physical framework. It suggests that our cosmic history doesn't just stop at a wall of infinite density, but has a deeper backstory written in the language of quantum physics. This is why exploring concepts like loop quantum gravity, string theory, and the holographic principle isn't just academic speculation. It's a necessary effort to peek behind the curtain of the singularity. By probing these ideas, we aren't dismissing the incredible success of the Big Bang model in describing the evolution of our universe. Instead, we are seeking to complete it, to understand the stage itself rather than just the play that has been performed on it for the last 13.8 billion years. So if the singularity of the Big Bang represents the point where our classical models fail, we must turn to a more complete theory, one that can handle the extreme quantum nature of reality at its smallest scales. This brings us directly to the quest for a theory of quantum gravity and to a truly mind-bending possibility. That time itself is not a fundamental feature of the cosmos, but something that emerges from a deeper, timeless layer of reality. It's a concept that feels almost impossible to reconcile with our daily experience, where time's arrow seems undeniable. Yet, some of the most promising approaches in modern physics point exactly in this direction. At the heart of this idea is the work of physicists John Wheeler and Bryce-DeWitt. In the 1960s, they attempted to apply the rules of quantum mechanics to the entire universe, leading them to a now famous equation that bears their names. The Wheeler-DeWitt equation is notoriously difficult to solve, but its implications are staggering. In this formulation, the wave function of the universe, a mathematical object that describes the probability of finding the cosmos in any particular state, does not evolve over time. The variable for time simply does not appear in the equation. It's as if the universe, in its most fundamental description, is frozen. It just is, a single, static entity containing all of what was, what is, and what will be in one timeless package. This perspective is often called the block universe theory. Imagine reality not as a movie playing out frame by frame, but as the entire film reel itself, complete and unchanging. From our limited perspective within the reel, we experience a single frame at a time, which we call the present, and we perceive the sequential projection of these frames as the flow of time. But from a God's eye view outside the reel, the entire story exists simultaneously. The past isn't gone, it's simply another part of the block. The future isn't unwritten, it's already there. This is the view championed by physicists like Carlo Rovelli, who argues that time is an illusion born from our imperfect, macroscopic perception of a world that is fundamentally quantum and relational. But how does our dynamic, ever-changing world arise from such a static foundation? The key lies in the quantum concept of probability amplitudes. In the pre-temporal quantum realm, the universe isn't described by a specific set of initial conditions, like a clock being wound up and set ticking. Instead, it's described by a range of possibilities, each with its own probability. The beginning is not a causal event but a quantum transition, a tunneling from nothingness into somethingness, governed by probability rather than a chain of cause and effect. Think of it like the spontaneous decay of a radioactive atom. We cannot predict the exact moment a single atom will decay. We can only assign a probability. In a similar way, the emergence of our space-time universe from a timeless state might be a quantum event, a fluctuation that became reality. This framework doesn't just offer a way to avoid the singularity. it provides a powerful new language for cosmic origins. It suggests that the question, why is there something rather than nothing, might be transformed into, why is the probability for something so high? In this timeless quantum landscape, the universe isn't created, it is actualized. The wave function of the universe encapsulates every possible history and geometry, and our specific, expanding, temporal cosmos is simply one particularly probable peak in that vast landscape of potential. This idea challenges our deepest intuitions about cause and sequence, but it offers a breathtakingly elegant key to unlocking the secrets of a cosmos that existed before time had a role to play. But if the wave function of the universe suggests a timeless, static block, how does that translate into the dynamic, expanding cosmos we actually observe? This brings us to one of the most compelling and visually intuitive theories that builds upon this quantum foundation: loop quantum cosmology. This framework offers a dramatic alternative to the traditional Big Bang story, replacing the terrifying singularity with a far more graceful and profound event, a cosmic bounce. Imagine our universe not as a one-time explosion from nothing, but as a phase in an endless cycle of expansion and contraction, like a cosmic lung breathing in and out for all eternity. In this model, the Big Bang wasn't a beginning, it was a rebirth. The key to this idea lies in the parent theory, loop quantum gravity, developed by physicists like Abhay Ashtekar, Lee Smolin, and Carlo Rovelli. This approach attempts to quantize spacetime itself. It proposes that space isn't a smooth, continuous fabric, as general relativity suggests, but is instead woven from tiny, indivisible loops, one-dimensional threads of gravitational field. Think of the fabric of reality as a finely knitted sweater. From a distance, it appears smooth and continuous, but up close, you see it's actually made of countless individual, interconnected loops. This granular structure of space has a profound consequence. There is a smallest possible unit of volume, a quantum of space, which means nothing can be compressed to an infinite density. This single idea shatters the concept of a singularity. This is where the magic happens. In the standard Big Bang model, if you rewind the expansion, all the matter and energy of the universe gets crushed into an infinitely dense point. But in loop quantum cosmology, you can only rewind so far. As the universe contracts towards what would have been the singularity, it reaches a point of maximum possible compression, the Planck density governed by the graininess of space. Instead of collapsing further into infinity, the immense gravitational energy of this compressed state creates a powerful repulsive force. It's like squeezing a rubber ball. You can compress it only so far before the internal pressure becomes too great and it pushes back, springing out of your hand. In this cosmic model, that spring is the Big Bang itself, or more accurately, the Big Bounce. During this bounce, as the universe transitions from a state of extreme contraction to expansion, it passes through a quantum phase. In this brief but crucial epoch, the classical notions of space and time dissolve. The orderly progression of moments breaks down into a fuzzy, probabilistic foam. Time as a measurable parameter loses all meaning. This pre-bounce era isn't a previous universe in a linear timeline with its own past and future. It exists in a timeless quantum realm, a superposition of possibilities from which our own universe crystallized. The bounce is not a moment in time but a bridge between two classical phases, a transition through a state where the very concepts of before and after are undefined. This elegant solution does more than just avoid a mathematical singularity. It completely redefines our cosmic origin story. It eliminates the need for an absolute beginning, suggesting that the cosmos may be eternally cyclic, with each bounce giving rise to a new expanding universe. Furthermore, the conditions of the quantum bounce could naturally seed the large-scale structure we see today, providing an explanation for the initial conditions that inflation theory was designed to address. It also opens the door to a multiverse scenario where each bounce might not perfectly reset the universe, potentially allowing for different physical constants or laws to emerge in each new cycle. This transforms the question of our universe's surprising suitability for life from a one-time mystery into a statistical probability across countless cycles. While loop quantum cosmology offers a compelling vision of a bouncing universe, another profound framework invites us to expand our horizons even further into the realm of extra dimensions and an infinite multiverse. String theory, one of the most ambitious attempts to unify all forces of nature, proposes that the fundamental constituents of reality are not point-like particles but incredibly tiny, vibrating strings. Their different vibrational patterns give rise to every particle and force we observe, but to be mathematically consistent, these strings require more than the 3 spatial dimensions and one time dimension we experience. They demand a reality woven from 10 or even 26 dimensions, most of which are curled up into a space too small for us to perceive. Within this lush, higher dimensional arena, the concept of a pre-temporal state transforms into something called the string theory landscape. Picture an vast, timeless, and multidimensional terrain of possibilities. Each valley, hill, and plateau in this landscape represents a unique, stable configuration of those extra dimensions, a specific set of physical laws and constants. Our universe, with its particular values for the strength of gravity, the mass of an electron, and the other fundamental numbers, is just one point in this colossal landscape. It is not special or central. It is simply one possibility among a number so vast it dwarfs the number of atoms in our observable universe. This is where the concept of brains becomes essential. Short for membranes, brains are dynamic objects within string theory that can have many dimensions. Our entire universe could be a 3-dimensional brain, a sort of cosmic island floating within a higher dimensional bulk space. In this framework, an event like the Big Bang might not be the birth of everything, but a local event on our brain, perhaps caused by a collision with another brain floating in the bulk. Time as we know it emerges and has meaning only within our specific brain, within our specific universe. The higher dimensional bulk itself, the true foundation of reality, could be utterly timeless. Universes nucleate within it like bubbles forming in an eternal, unchanging glass of champagne, each with its own internal clock that starts ticking only from the perspective of those inside the bubble. This elegant framework, championed by physicists like Leonard Susskind, provides a stunningly natural explanation for one of the greatest mysteries in cosmology, the apparent fine-tuning of our universe for life. The constants of nature seem perfectly and improbably calibrated to allow for galaxies, stars, planets, and ultimately, us. In a single universe model, this cries out for an explanation, a designer, or a staggering coincidence. But in the string theory landscape, it becomes a statistical inevitability. With a near-infinite number of universes, each with randomly different physical laws, it is no wonder that at least one universe, by pure chance, ended up with the right conditions for life. We don't live in a fine-tuned universe. We live in a universe that is habitable, and therefore we are here to observe it. This principle, known as the anthropic principle, shifts the question from why are the constants so perfect to in which of the many possible universes do we find ourselves. This perspective doesn't diminish our cosmos. It embeds it within a grander, more majestic meta-reality. The search for a pre-temporal beginning is no longer about finding a first moment for a single timeline. but about understanding the timeless, higher dimensional structure from which all possible timelines eternally blossom. It invites us to think on a scale that is almost incomprehensible, where our entire history is just a single note in an endless, silent symphony of existence. This radical reimagining of time doesn't just live in the equations of physicists. It sends shockwaves through the very foundations of philosophy, forcing us to confront questions about free will, the nature of consciousness, and what it truly means to exist. If the block universe model is correct, if all of time is laid out in a single, fixed four-dimensional structure, then our most deeply held intuitions about reality begin to unravel. The feeling that we are moving through time, making genuine choices that shape an open future, could be the most persuasive illusion of all. This isn't a new anxiety. It's a dilemma that has haunted thinkers for millennia, and modern cosmology is now providing a startling new context for this ancient debate. We can trace this line of thought all the way back to the pre-Socratic philosopher Parmenides in ancient Greece. He argued passionately that change, motion, and the very passage of time were logical impossibilities, mere illusions presented to us by our fallible senses. For Parmenides, true reality was the one, an eternal, unchanging, indivisible, and timeless whole. He believed that the appearance of a world in flux was a deceptive story we tell ourselves, while the underlying truth was a static, perfect unity. In a fascinating twist, the block universe theory of modern physics resurrects this ancient idea, dressing it in the mathematical language of general relativity and quantum mechanics. Parmenides 1 finds a strange echo in the four-dimensional spacetime continuum, where everything that ever happens or will happen simply is. This has immediate and profound consequences for our understanding of causality, the bedrock of science itself. Causality is the idea that one event brings about another. A cause must always precede its effect, but in a timeless block universe, the concepts of before and after are just relative perspectives within the structure. Every event is equally real and permanently fixed in its relationship to every other event. The Big Bang doesn't cause the formation of galaxies in a linear sense. Both are just parts of the whole, eternally connected by the geometry of the continuum. This doesn't destroy the laws of physics, it embeds them. The laws don't govern events unfolding in time. They describe the intricate, fixed patterns that relate all events across the entire block. It's the difference between watching a sculptor create a statue step by step and simply observing the finished sculpture itself. The process of creation is gone, but the relationships between the statue's parts are permanently and beautifully defined. This leads us directly to the unsettling question of free will. If the future is already out there, as real and unchangeable as the past, then in what sense are our choices free? It feels as though we are authors writing our life stories, but the block universe suggests the book is already complete. We are simply readers, turning the pages and experiencing each chapter in sequence, mistaking our reading for writing. Modern philosophers like Hugh Price grapple with this. He points out that this view doesn't necessarily make us powerless automatons. It might just mean we need to redefine what free will means. Perhaps our decisions and deliberations are real processes within the block. They are the very mechanisms by which the fixed story plays out. Your choice to watch this video was inevitable given the state of the universe a moment ago, but your process of reasoning was an essential part of that inevitable chain. It's a compatibilist view. Our internal experience of choice is real and meaningful, even if the ultimate outcome is predetermined within a larger structure. Finally, this challenges our very sense of identity. We typically think of ourselves as a continuous narrative, a thread of consciousness that stretches from our childhood to the present. But if time is not fundamental, this narrative is a construction. The you from 10 years ago and the you of this moment are distinct events in the spacetime block, connected by memory and causation, but not fundamentally the same entity experiencing a flow. This idea is echoed in Buddhist philosophy, which also questions the permanence of the self, viewing it as a temporary assemblage of ever-changing parts rather than a solid, enduring soul. A timeless cosmos suggests that all versions of you, from your first breath to your last, exist eternally. This can be a frightening thought, evoking a sense of fatalism, or it can be a liberating one, a perspective that all moments of joy, love, and discovery are forever preserved in the fabric of reality, never truly lost to the past. It forces us to reconsider what it means to be and invites a profound dialogue between the cold, hard truths of physics and the deepest mysteries of human experience. If the universe at its most fundamental level is truly timeless, then we need a language to describe it that is itself free from the constraints of time, a system of truth that is eternal, unchanging, and independent of any particular moment or place. Remarkably, we already have such a language, and we use it every day: mathematics. The number pi is the same today as it was 1 billion years ago, and will be 1 billion years from now. The Pythagorean theorem doesn't evolve or age. It simply is, holding true regardless of when or where it is discovered. This uncanny ability of math to describe the physical world with such precision has led some of the brightest minds in physics to propose a truly breathtaking idea: that the universe isn't just described by mathematics, but that it is mathematics. This is the core of the mathematical universe hypothesis, most famously championed by the cosmologist Max Tegmark. Tegmark's hypothesis pushes this idea to its ultimate conclusion. He suggests that our physical reality isn't just modeled well by mathematical structures, it is a mathematical structure. In this view, every particle, every force field, every ripple of spacetime, and even the consciousness experiencing it all, are not made of some mysterious physical substance. Instead, they are entirely mathematical entities, patterns, and relationships within an abstract, formal system. Think of it like a computer game. The world on your screen seems real and dynamic, with mountains, characters, and weather. But at its core, it's all just code ones and zeros, variables and algorithms being processed. The mathematical universe hypothesis proposes that our reality is the same. The convincing, physical stuff we interact with is merely a representation. The underlying reality is pure, timeless math. This perspective offers a stunningly elegant way to conceptualize the pre-temporal state we've been exploring. Before time, before space, before any physical laws, there was, and eternally is, the abstract landscape of mathematics. This is a modern echo of Plato's theory of forms, which held that the physical world is a shadow of a higher, perfect realm of ideal concepts and geometric forms. The pre-temporal universe, then, isn't a void or a quantum foam waiting to erupt. It is this Platonic realm of mathematical truths. Our specific universe, with its particular set of physical constants and laws, is just one specific mathematical structure that has been instantiated. It's one particular equation or set of equations that has a solution complex enough to contain self-aware subsystems, beings like us who can observe it and wonder about it. We can find clues to this mathematical foundation in advanced fields like group theory and topology. Group theory is the mathematical study of symmetry. It provides a language for describing how objects can be transformed while keeping their essential properties unchanged. The standard model of particle physics, which describes all known fundamental particles and forces, is built upon specific symmetry groups. These groups, with names like SU3 and SU2, dictate how particles can interact and transform into one another. Crucially, these groups exist as abstract mathematical concepts, completely independent of time. They describe a web of possible relationships, a timeless architecture of potential interactions that our universe simply obeys. Topology, often called rubber sheet geometry, is even more fundamental. It studies the properties of space that remain unchanged under continuous stretching or bending properties like connectedness or the number of holes in a shape. A coffee mug and a donut are topologically equivalent to a topologist because each has exactly one hole. This field allows physicists to model the very shape of space itself in the pre-temporal realm. The initial conditions of the cosmos might not be a set of numbers in a vacuum but a specific topological structure, a particular geometric form that, when understood mathematically, inevitably gives rise to the dynamics we perceive as spacetime expansion, particle creation, and the arrow of time. The Big Bang, in this view, could be the moment this timeless mathematical structure began to express itself in a way that includes a dimension we experience as time. This radically shifts the goal of physics. Instead of discovering the fundamental building blocks of matter, the ultimate quest becomes the discovery of the correct mathematical structure that corresponds to our reality. Physics is reduced to a kind of archaeology in the Platonic realm, an effort to uncover the eternal equations that we are embedded within. It implies that the cosmos hasn't always existed in a temporal sense, but that it exists in a mathematical sense which is beyond time altogether. There was no first moment because the concept of moment is a property that emerges from the structure itself, not a prerequisite for it. In this breathtaking vision, mathematics is not just the language we use to describe the universe, it is the source code of reality, and the pre-temporal realm is the infinite library where all possible codes are eternally written. But if the universe is a timeless mathematical structure, how do we get from that silent, eternal perfection to the vibrant, churning, dynamic reality we experience? The bridge between the abstract and the physical, between the timeless and the temporal, may be found in one of the most bizarre and well-verified phenomena in all of physics: quantum fluctuations. We often hear that in the quantum vacuum, even in what we call empty space, pairs of virtual particles and antiparticles spontaneously pop into existence, only to annihilate each other an instant later. This isn't just theoretical, it's been confirmed experimentally through measurable effects like the Casimir force. But this description is steeped in the language of time. They pop in and pop out. So how could such a process possibly operate in a pre-temporal state, where there is no before or after for these events to happen in? The key is to radically reinterpret what a quantum fluctuation truly is when we strip away the dimension of time. We must stop imagining it as an event and start thinking of it as a relationship. In the standard temporal view, the vacuum is not a static nothingness. It's a seething sea of potentiality with a certain energy level. The Heisenberg uncertainty principle, which states that we cannot precisely know both the energy of a system and the exact time of its measurement, allows for brief borrowings of energy from the vacuum. These borrowings manifest as particle pairs, but in a timeless framework, the uncertainty principle isn't about energy and time. It's about the fundamental fuzziness and probability that are inherent to reality at its core. The fluctuations aren't happening, they simply are. They are static, timeless patterns of probability, permanent features of the quantum vacuum's architecture. A powerful way to visualize this is with the concept of quantum foam, an idea dating back to John Wheeler. Imagine the foundational layer of reality not as a smooth, flat plane, but as a frenetic, bubbling foam like the head on a glass of beer. Each bubble in this foam is a tiny, fluctuating distortion of spacetime itself. In our temporal universe, this foam is dynamic, with bubbles constantly forming and dissolving. But from a pre-temporal perspective, the foam is just like that. It is a fixed, intricate geometry of connectivity and chaos. There is no process of formation. The frothy, probabilistic structure is the eternal and fundamental state. The potential for every possible particle, every possible universe, is encoded in the timeless relationships between the bubbles of this foam. This is where the genius of Stephen Hawking and his collaborator James Hartle made a monumental contribution. They applied this very idea to the origin of the entire cosmos. In their model, the universe can be described by a wave function that encompasses all possible histories and geometries. The transition from nothingness to somethingness isn't a causal chain of events. It's a quantum tunneling effect. Think of it like this. If you roll a ball up a hill, classical physics says it will roll back down unless it has enough energy to go over the top. But quantum mechanics allows for a bizarre possibility. There's a tiny, non-zero probability that the ball could simply tunnel straight through the hill and appear on the other side without ever having had the energy to climb it. It doesn't travel through the hill in a path. It just has a probability of being on the other side. Hawking and Hartle proposed that the universe did exactly this. The nothingness of the pre-temporal vacuum is one side of the hill. A vast, expanding universe like ours is on the other side. There is no moment of creation, no first cause, no need for a creator. There is simply a probability amplitude, a calculation within the wave function of the universe for this specific tunneling event to have occurred. The Big Bang, then, is not a fiery explosion in a void, but the moment this timeless quantum probability became our specific classical reality. It's the point where the fuzzy, probabilistic quantum description of the cosmos crystallizes into the definite, expanding space-time we now inhabit. In this view, the question, why is there something rather than nothing, is transformed. The answer is not found in a cause, but in a calculation, because the quantum probability for something is overwhelmingly high. The origin of the cosmos becomes a statistical inevitability, a peak in the landscape of possibility that was almost certain to be actualized. This doesn't make our existence any less miraculous. It grounds that miracle not in mystery, but in the deepest, most fundamental laws of nature. So we've seen how quantum fluctuations in a timeless vacuum could provide the seed for our entire cosmos. But what if that process wasn't a one-time event? What if it's happening endlessly forever, giving rise not just to one universe, but to an infinite number of them in a ceaseless, self-replicating frenzy? This is the breathtaking vision of eternal inflation, a theory that takes the idea of a pre-temporal cosmos and scales it up to its ultimate, mind-boggling conclusion. It proposes that our universe is merely one bubble in a vast, frothing ocean of universes, each with its own laws of physics, forever budding off from an inflating meta-reality that truly has no beginning and no end. The story of eternal inflation begins with the more familiar concept of cosmic inflation, most famously developed by physicist Alan Guth. Inflation solves several major puzzles in cosmology by proposing that the very early universe underwent a period of exponentially rapid expansion, smoothing it out and seeding the tiny density variations that would later grow into galaxies. But Guth and others, particularly the Russian physicist Andrei Lind, soon realized something extraordinary about this inflationary mechanism. Under the right conditions, once inflation starts, it might never stop. It could become eternal. Here's how it works. Think of the inflating universe not as a single, homogeneous entity, but as a field of energy, often called the inflaton field. This field is like a vast, rolling landscape of hills and valleys. The valley represents a low-energy state, a stable, calm universe like our own after inflation ended. But to get there, the field has to roll down from a high-energy plateau. Now, due to the bizarre rules of quantum mechanics, this field is constantly experiencing tiny fluctuations. In most regions of space, the field will indeed roll down into the valley, ending inflation and giving birth to a stable pocket universe like ours. But here's the magical part. In some regions, a quantum fluctuation will kick the inflattened field back up the hill to a higher energy state. In those regions, the rate of inflation actually increases. So space in those tiny patches expands at an even more furious rate. This creates a self-sustaining cycle. The overall inflating background space is expanding exponentially. Within it, countless regions quantum fluctuate down into valleys, becoming stable bubble universes. But other regions fluctuate upward, and those areas inflate even faster, ensuring that there is always more inflating space than there is space that has stopped inflating. The process never runs out of fuel. It's like a chain reaction that can never be quenched, a fire that creates more kindling faster than it can burn it. This leads to a staggering picture of reality. There is no first bubble, no first moment of creation for the multiverse as a whole. The inflating background, the so-called multiverse substrate, is eternal into the past and will be eternal into the future. From our perspective inside one of the bubbles, we see a definite beginning, our Big Bang, which is the moment our bubble formed and inflation ended inside it. But that is just a local event. From the perspective of the wider multiverse, bubbles are constantly nucleating forever. The meta-reality that contains this endless inflation is the true pre-temporal state. It is a dynamic, ever-growing arena, but it may not have its own global time. Time, as we understand it, only has meaning within each individual bubble universe once it forms. The background exists in a state where the concepts of before and after are relative, applying only to the internal clocks of its countless offspring. This model provides one of the most compelling and natural explanations for the existence of our universe. We don't need to ask why the universe exists. We only need to explain why our particular universe exists within an infinite ensemble. In an eternally inflating multiverse, every possible set of physical constants and laws will be realized in some bubble universe somewhere. We find ourselves in one with the right conditions for life, not because it was designed, but because it is one of the few habitable possibilities in an unimaginably vast and varied cosmic landscape. Eternal inflation doesn't require a creator or a unique beginning. It simply emerges from the relentless, timeless mechanics of quantum fields and expanding space, offering a vision of cosmic origins that is both humbling and magnificently elegant. Now, if the universe can emerge from a timeless quantum foam, and if eternal inflation can spawn countless bubbles, we must ask a more fundamental question: what is the most basic currency of reality? What is the ultimate stuff from which space, time, and matter are forged? The answer proposed by one of the most radical ideas in theoretical physics is both simple and profound: information. And this leads us directly to the holographic principle, a concept that not only redefines the nature of our cosmos, but offers a stunningly novel perspective on how it could have originated from a timeless, lower-dimensional data structure. The story of the holographic principle begins not with the beginning of the universe, but at the edge of one of its most mysterious endpoints, a black hole. In the 1970s, physicist Jacob Bekenstein made a startling discovery. He realized that a black hole's entropy, a measure of its hidden information or disorder, is not proportional to its volume, as you might expect for a three-dimensional object. Instead, it is proportional to the surface area of its event horizon, the two-dimensional boundary from which nothing can escape. This was a huge clue. It suggested that all the information describing everything that ever fell into the black hole, every star, every planet, every book, was not lost inside its vast volume but was somehow encoded on its two-dimensional surface. Stephen Hawking later showed that black holes slowly evaporate, radiating away their energy and seemingly destroying that information, which created a paradox. If information is lost, it violates a fundamental tenet of quantum mechanics. This black hole information paradox sparked a decades-long crisis in physics. The resolution, championed by theorists like Leonard Susskind and Gerard T. Hooft, was to take Bekenstein's idea utterly seriously. They proposed that this wasn't just a quirk of black holes, it was a fundamental property of reality itself. The holographic principle boldly states that all the information needed to describe a volume of space can be entirely encoded on its lower dimensional boundary. Our familiar three-dimensional world, with its depth and substance, is a projection, a holographic illusion arising from a vast, complex data processing happening on a distant, two-dimensional surface. We are not living in a universe, we are living on a cosmic hard drive. Apply this breathtaking idea to our quest for a pre-temporal origin, and the implications are staggering. If our four-dimensional spacetime universe 3 of space, 1 of time, is a holographic projection, then the source code for that projection must exist on a lower dimensional surface that itself exists outside of our spacetime. This boundary is often called the timeless horizon. It is not a physical place you could travel to. It is a mathematical surface where the information that defines our reality is stored. Crucially, this data surface is not evolving in time. It is static, complete, and eternal. The relationships between the bits of information on this surface are fixed, much like the patterns of ink on a page are fixed. The story doesn't change, the page just is. So how do we get from this timeless, two-dimensional date a page to our dynamic, expanding, four-dimensional cosmos? The process is one of translation and projection. The Big Bang in this holographic view is not an explosion in space, but the moment this timeless information became translated into a spatial geometry. It is the instant the cosmic projector was switched on, converting the static code on the boundary into the dynamic movie we experience. The dimension we perceive as time is not fundamental. It emerges from the way this data is read and processed. The entire history of our universe, from the first instant to the last star burning out, is simultaneously and eternally present on that boundary. Our experience of a flowing present is just our localized perspective within the projected hologram. This provides a beautifully elegant solution to the problem of a beginning. There is no need for a first moment because the information describing every moment is equally present on the timeless horizon. The question, what happened before the Big Bang, becomes as nonsensical as asking what happened on a DVD before the movie started. The information for the entire movie is present on the disc from the outset. Hitting play doesn't create the story. It simply begins the process of projecting it sequentially. In the same way, the Big Bang is the play button for our universe, initiating the projection from a data set that has always existed in a timeless Platonic state. This framework doesn't just merge quantum gravity with information theory. It suggests that information theory is the more fundamental language, and that the cosmos, at its heart, is a timeless computation rendering a breathtakingly realistic simulation of space, time, and matter. But if the holographic principle suggests our universe is a projection from a timeless data surface, another pair of visionary physicists offered an equally elegant and perhaps even more visually intuitive model for how time itself could emerge from a state of pure geometry. This is the no-boundary proposal put forward by James Hartle and Stephen Hawking. and it represents one of the most beautiful and self-contained descriptions of cosmic origins ever conceived. Their idea was to completely eliminate the problem of the Big Bang singularity, not by replacing it with a bounce or a bubble, but by mathematically rounding it off, transforming a sharp, jagged beginning into a smooth, curved origin, an origin without an edge, and therefore without a boundary in time. To understand how this works, we need to take a brief but fascinating detour into a different kind of geometry. We are all familiar with the geometry of our everyday world, described by the ancient Greek mathematician Euclid. In Euclidean geometry, parallel lines never meet. The angles of a triangle always add up to 180 degrees and space is flat. This is the geometry of our intuition. But general relativity showed us that the real geometry of the universe is non-Euclidean. It's curved by mass and energy. Hartle and Hawking took this a step further. To solve the problem of the beginning, they proposed that in the very earliest moments, the universe was governed by yet another type of geometry, Euclidean quantum gravity. In this approach, time undergoes a miraculous transformation. The familiar dimension of time, with its clear distinction between past and future, is replaced with what physicists call imaginary time. This sounds like science fiction, but it's a precise mathematical trick. Imagine time as we know it is a horizontal line, with the past on the left and the future on the right, and the Big Bang singularity is a sharp point at the far left where the line begins. This is the boundary, the ultimate starting point that physics cannot penetrate. Now, Hartle and Hawking's proposal is to take that sharp point and gently bend the entire timeline, curving it into a smooth, continuous arc. When you do this, the dimension of time becomes more like a dimension of space. It loses its arrow and its singular beginning. The most famous analogy for this is the Earth itself. If you ask what is north of the North Pole, the question has no meaning. The North Pole is not an edge of the planet. It is simply a point where the concept of north ceases to be defined. The Earth's surface is finite in area, yet it has no boundary, no edge you can fall off. The no-boundary proposal suggests the universe is exactly like this, but in 4 dimensions. So what does this mean for the origin of everything? It means there is no before the Big Bang, because there was no time for anything to be before in. The universe would be described as a smooth, 4-dimensional, closed geometric shape like a sphere. The Big Bang is not a point on this shape, it is a point of this shape, analogous to the Earth's South Pole. As we move away from that point in any direction, the universe expands, and the familiar distinction between space and time gradually crystallizes. In this model, the universe doesn't pop into existence at a moment in time. It just is in a complete, self-contained, and finite geometric form. The entire history of the cosmos, from this smooth, timeless origin to its potentially infinite future, is wrapped up in a single, elegant mathematical object. This resolves the singularity problem with breathtaking grace. There is no point of infinite density because the geometry is always smooth and well-behaved. The laws of physics never break down. The proposal doesn't require any external cause or pre-existing state because the universe is its own cause. It is self-contained. The question of what happened before the Big Bang is rendered obsolete, much like asking what's south of the South Pole. The proposal provides a natural, scientific account of creation ex nihilo, creation from nothing where the nothing is not an empty void, but the absence of space-time itself. The universe emerges from a pure, timeless geometry, a state of such profound simplicity that it requires no further explanation, offering a powerful and profoundly satisfying vision of how everything could have come from nothing at all. While modern physics uses equations and quantum probabilities to describe a pre-temporal state, humanity has been wrestling with this profound concept for millennia, weaving it into the very fabric of our oldest stories and spiritual traditions. Long before Hawking or Ashtekar, our ancestors gazed into the heavens and intuitively sensed that the origin of all things must lie beyond the simple tick of a clock, in a realm untouched by time. This deep, shared intuition is etched into the creation myths and religious texts of cultures across the globe, revealing a universal human quest to comprehend existence from a standpoint outside of time itself. Consider the opening lines of the book of Genesis, familiar to many. It begins with the phrase, "in the beginning," but this immediately presents a fascinating puzzle. The very first word, "in," implies a container, a framework of time that already exists for this beginning to happen within. Some theological and philosophical interpretations suggest this famous beginning is not the absolute start of time, but rather the moment time, as we understand it, was organized out of a pre-existing formless state. The verse continues to describe the earth as without form and void, and darkness covering the face of the deep. This imagery powerfully evokes a kind of primordial, chaotic potential, a timeless, undifferentiated state of pure possibility that the divine then acts upon. It's not a narrative of creation from absolute nothingness, but a story of ordering and giving form to a pre-temporal, watery chaos, a concept that resonates deeply with the quantum foam or the string theory landscape we discussed earlier. This theme of a formless, eternal precursor is even more explicit and elaborate in Eastern traditions. In Hinduism, the ultimate reality is Brahman, an infinite, eternal, unchanging, and timeless ground of all being. Brahman is not a god who creates in time. It is the very substance of reality itself, from which time, space, and the illusion of a changing world, Maya, emerge. The cosmos undergoes endless cycles of creation, preservation, and dissolution, but Brahman itself remains untouched, the silent, timeless witness to it all. This is a stunningly precise metaphysical counterpart to the scientific concept of a timeless quantum vacuum, or a multiverse substrate from which individual universes with their own time arrows continually bubble forth and dissolve back. The Hindu concept of a cyclical cosmos without a definitive beginning or end finds a powerful echo in the bouncing universes of loop quantum cosmology. We find similar threads in the ancient myths of Egypt and Greece. The Egyptian creation myth from Heliopolis describes a primordial ocean of chaos called Nun, a dark, infinite, and timeless watery abyss that existed before the first god, Atum, willed himself into existence. Nun wasn't a place in time, it was the negation of time and form, the utter void from which order and sequence emerged. Similarly, the Greek poet Hesiod, in his Theogony, begins with chaos, not merely disorder, but a gaping void, a yawning chasm that predates the gods themselves. From this chaos, the first deities like Gaia, Earth, and Eros, Desire, emerge, setting the stage for the cosmos. These myths don't start with a bright, clear genesis. They start in the murky, indefinable realm of the pre-temporal, a state of potential that must be shaped and ordered into the world we know. Indigenous cultures around the world also hold rich cosmologies that often emphasize cyclical time and eternal return rather than a linear, one-time beginning. Many Native American traditions, for instance, speak of worlds that exist in cycles, with each world emerging from the one before it, often after a period of purification or transformation. The beginning of a cycle might be triggered by events within a timeless dreamtime, a concept from Australian Aboriginal culture that refers to a sacred, eternal time of creation that is not linear but always present, underlying and interpenetrating our everyday reality. These perspectives challenge the Western linear timeline and align more closely with the scientific view of a universe without a true starting point, where time is a local phenomenon within a larger, eternal framework. This incredible cross-cultural consistency is not a coincidence. It points to something fundamental about human consciousness and our attempt to make sense of our place in the universe. Faced with the mystery of existence, the human mind, whether through the language of myth, religion, or science, repeatedly arrives at the same profound conclusion: that the tidy sequence of cause and effect we experience in our daily lives cannot be the whole story. There must be a deeper reality, a ground of being that transcends time, from which our temporal world unfolds. These ancient narratives are not primitive attempts at science. They are profound philosophical and poetic explorations of the same mystery that drives modern cosmology. They represent the human psyche grappling with the limits of its own temporal perspective, reaching for a truth that lies just beyond the horizon of time itself, reminding us that the quest to understand a pre-temporal cosmos is one of the oldest and most enduring journeys of the human spirit. Yet if the fundamental nature of reality might be a timeless block or a static mathematical structure, we are immediately confronted with one of the most puzzling contradictions in all of science and philosophy. Why does our lived experience feel so utterly different? Why do we perceive a relentless one-way flow from past to future, a vivid stream of moments where the past feels fixed, the present feels immediate, and the future feels open and unknown? This powerful, undeniable sensation of temporal flow is so ingrained in our consciousness that the idea of it being an illusion feels not just counterintuitive, but almost impossible to accept. The resolution to this paradox lies not in the laws of physics, but within the intricate wiring of our own brains. Our perception of time is not a direct window into fundamental reality. It is a brilliant, complex construction, a biological adaptation crafted by evolution to help us navigate the world, not to comprehend its ultimate nature. Neuroscientists and psychologists believe that the brain does not have a single, dedicated time organ, like it has an eye for sight or an ear for sound. Instead, our sense of time is a distributed masterpiece of neural computation, woven together from various cognitive processes. Two of the most crucial ingredients in this recipe are memory and anticipation. Think of your conscious experience right now. You are not perceiving an infinitesimally thin sliver of now. What you feel as the present moment is actually a slightly extended window, a psychological phenomenon famously called the specious present. It's a rolling integration of the very recent past, the current sensory input, and a constant, low-level prediction of the immediate future. When you listen to a melody, you don't hear a series of isolated notes. Your brain stitches them together into a phrase. The note that just passed is held in your working memory, seamlessly connected to the note you are hearing now, which itself primes you to anticipate the note that should come next. This blending creates the smooth, continuous flow of auditory experience. This is how all of time is built for us, not as a series of frozen instants, but as a cohesive narrative. This narrative is fundamentally story-driven, and the chief editor of that story is memory. Your memory system is not a perfect, high-fidelity recorder. It is an active, reconstructive process. When you recall an event, you are not playing back a video file. You are reassembling fragments of information, often filling in gaps with logical assumptions or even outright fabrications, all to create a coherent and useful timeline of your past. This timeline is essential for creating the illusion of a past that is distinct from the present. Without this constantly updating library of autobiographical memory, our experience would be a chaotic jumble of disconnected moments, with no thread to connect them into a personal history. The past feels fixed and gone precisely because our memory labels it as such, storing it in a different mental category than the live feed of our current sensory input. But the brain is not just looking backward, it is perpetually looking forward. Anticipation and prediction are perhaps the most important jobs your brain does. To navigate the world effectively, to catch a ball, to have a conversation, to avoid a stepping off a curb into traffic, your brain must constantly forecast what is about to happen. This is known as predictive processing. Your brain is a prediction engine running millions of simulations based on past experience to prepare your body and mind for the next moment. This relentless forward momentum, this state of always being about to, is a powerful contributor to our feeling that time is moving forward. The neuroscientist Dean Buonamano, in his excellent book Your Brain is a Time Machine, argues persuasively that our perception of time's flow is a side effect of these neural circuits for memory and prediction engaging in a constant dialogue. The brain compares its predictions to the incoming sensory data, and the slight mismatch between what it expects and what actually happens creates the subjective sensation of a present moment that is perpetually updating, perpetually flowing into the next. This has a profound implication. The arrow of time we feel so viscerally may be largely a property of our psychology, not of the universe. It is a useful illusion. For a living organism, understanding causality is a matter of survival. Knowing that the sound of a twig snapping the cause likely means a predator is approaching the effect is far more important than understanding the block universe. Our brains have therefore evolved to impose a strong cause and effect structure on reality, which inherently requires a clear ordering of events, a past where causes lie, and a future where their effects will unfold. This biological lens filters the timeless reality of physics into the urgent, sequential drama of our lives. The pre-temporal universe isn't hidden in some distant galaxy. It is hidden behind the very cognitive machinery we use to perceive the world. We are like characters in a movie who believe the story is unfolding in real time, unaware that the entire film already exists, complete and entire on the reel. Our struggle to conceive of a reality without time is not a failure of imagination. It is a limitation of our biological hardware, which was optimized for finding food and avoiding danger on the African savanna, not for contemplating the quantum origin of the cosmos. All of this theoretical brilliance would remain a fascinating thought experiment if it weren't for one crucial question: how do we actually test it? How can we possibly gather evidence for a reality that existed before time itself, a state that by its very definition seems to lie forever beyond the reach of empirical observation? This is the monumental challenge facing cosmologists today, but it's not an insurmountable one. While we may never take a direct photograph of the pre-temporal realm, its echoes and fingerprints might be imprinted all around us, hidden in the oldest light in the universe and in the faintest ripples in the fabric of spacetime. The search for these clues transforms the quest from pure metaphysics into a hard-nosed, data-driven scientific endeavor. Our most powerful time machine for peering into the primordial past is the cosmic microwave background, or CMB. This is the faint afterglow of the Big Bang, a bath of microwave radiation that fills every corner of the sky, released when the universe was just 380,000 years old and finally became transparent to light. This ancient light is a snapshot of the infant cosmos, and encoded within its subtle temperature variations, those tiny hot and cold spots, is a wealth of information about the conditions that existed in the first fraction of a second after the Big Bang. But if theories like the Big Bounce or eternal inflation are correct, the seeds for those patterns weren't planted after the bang, they were inherited from a pre-existing phase. A universe that bounced from a previous contraction, for instance, might carry over specific patterns or correlations from its prior incarnation. These would manifest as strange, anomalous features in the CMB that the standard inflationary model cannot explain. Scientists are meticulously scouring the data from missions like the Planck satellite, searching for exactly these kinds of statistical oddities. They're looking for imprints of a pre-Big Bang era, such as preferred directions in the universe that would break the assumption of overall uniformity, or specific patterns of polarization in the CMB light that could only be caused by primordial gravitational waves generated in a quantum bounce. Finding such a signature would be like discovering a fossilized seashell on a mountain peak, irrefutable evidence that the landscape was once underwater. It would strongly suggest our universe was shaped by events that occurred before what we call the beginning. Another tantalizing possibility involves the ultimate fate of the universe. If we are in a cyclic model, the precise rate of the universe's expansion and the amount of dark energy it contains might determine whether another big bounce is possible. By measuring these parameters with exquisite precision, we could gather indirect evidence that our cosmos is part of an eternal cycle of death and rebirth. Beyond the CMB, the next great hope for probing the pre-temporal realm lies in observing gravitational waves. These ripples in space-time, first detected by LIGO in 2015, are messengers from the most violent events in the universe, like colliding black holes. But there is a hypothetical background of gravitational waves that is far older and far more subtle, a primordial hum left over from the universe's inception itself. Future observatories like the Space-Based Laser Interferometer Space Antenna, or LISA, will be sensitive enough to tune into this faint cosmic symphony. The frequency and pattern of these primordial waves could tell us a tremendous amount about the universe's first moments. Crucially, if the universe underwent a bounce, the gravitational wave background would have a distinctive signature very different from one predicted by a single, one-time inflationary burst. Detecting the wrong kind of hum would force us to completely rewrite our cosmic origin story. On an even more fundamental level, experiments are underway to test the very nature of space-time and see if it indeed possesses the granular, quantum structure predicted by theories like loop quantum gravity. This graininess, if it exists, would become apparent at incredibly small scales, the so-called Planck length. While we can't build a microscope that powerful, we might observe its effects indirectly. Some theories suggest that this quantum foam could slightly alter the way light travels across the vast distances of the universe. Ultra-high-energy gamma rays from distant quasars or gamma-ray bursts could serve as probes. If the speed of light is ever so slightly different for different light frequencies due to this spacetime foam, our telescopes might be able to detect it. Finding evidence that space is not smooth and continuous but pixelated would be a monumental step toward validating the theories that allow for a pre-temporal phase, as it would provide the physical mechanism that prevents a true singularity and enables a bounce or a quantum transition. The pursuit doesn't end there. Particle accelerators like the Large Hadron Collider are, in a sense, recreating the conditions of the very early universe by smashing particles together at nearly the speed of light. While they can't reach the energy levels of the Planck epoch, they can provide crucial insights into the symmetries and forces that would have been at play. Any discovery of new physics, new particles, or unexpected interactions helps theorists refine their models of what happened in that first fleeting moment, tightening the constraints on what is possible and bringing us closer to understanding the transition from a timeless state to a temporal one. This practical, empirical hunt for evidence ensures that the captivating idea of a pre-temporal universe remains firmly rooted in the scientific method, a daring hypothesis being put to the test by our most advanced technology, bringing us closer than ever to answering humanity's oldest question. This expansion into the multiverse fundamentally reframes our entire search for a beginning. If our cosmos is just one of countless universes, then the question of its origin transforms from a singular mystery into a local event. Each individual universe within this vast ensemble may indeed have its own clear starting point, a big bang that sets its internal clock ticking. But the multiverse as a whole, the meta-reality that contains all of these cosmic bubbles, might have no such beginning. It could simply exist eternally and necessarily as a timeless background from which individual timelines perpetually emerge. This elegant shift in perspective doesn't just add more universes to the equation. It completely dissolves the philosophical problem of a first cause by placing it within an infinitely broader context. We can explore this idea through several compelling multiverse theories, each painting a slightly different picture of this timeless meta-reality. The most famous is perhaps the inflationary multiverse we discussed earlier, born from the theory of eternal inflation. Imagine an infinite, ever-expanding ocean of high-energy space, the inflatoned field. Within this ocean, quantum fluctuations constantly cause bubbles to nucleate. Each bubble is a region where inflation has ended, allowing a stable, low-energy universe like our own to form and develop its own laws of physics. From our perspective inside one bubble, we see a definite beginning, our Big Bang. But from the perspective of the inflating ocean, the process has no start and no end. Bubbles are always forming forever. The inflating background is the true pre-temporal state. It is eternal, and time as a global concept simply does not apply to it. There is no clock ticking for the entire multiverse. Then there is the quantum many-worlds interpretation, which offers a different but equally timeless vision. In this view, every time a quantum event occurs with multiple possible outcomes, like an electron being measured as spinning either up or down, the entire universe doesn't choose one outcome. Instead, it splits into multiple branches, each containing one of the possible results. This isn't a physical splitting like a cell dividing, but a branching of reality itself into parallel, non-communicating timelines. Crucially, this branching is not an event that happens in time. From a God's eye view outside the system, all possible branches exist simultaneously in a vast, static structure often called the multiverse wave function. Our conscious experience of moving along a single, linear timeline is just a peculiarity of our perspective within one specific branch. The entire, branching tree of possibilities exists at once, complete and entire. This is a profoundly timeless picture. The multiverse doesn't evolve, it just is. The illusion of change and sequence is confined to the observers within each individual branch. A powerful analogy to hold in your mind is that of a growing fractal tree, perhaps a mighty oak. Imagine each leaf on this tree represents a single, complete universe with its own entire history. The stem connecting the leaf to a branch represents that universe's timeline, from its Big Bang to its eventual end. Now, if you were a tiny creature living on one leaf, you would experience a clear beginning, middle, and end to your story. You would believe your leaf stem was the entire trunk of the tree, but if you could step back and see the whole tree, you would realize that your leaf is just one of countless others. The tree itself has no single beginning. Its growth is not a linear process from a first leaf to a last. It grows in all directions, constantly sprouting new leaves and new branches from its eternal, foundational structure. The trunk and roots of the tree, the source of all the branches, represent the timeless meta-reality. They aren't in time, they are what gives rise to time for every individual leaf. There is no first leaf on this tree, just as there is no first universe in an eternal multiverse. This perspective offers a stunning and elegant resolution to the ancient philosophical puzzle of the first cause. For centuries, thinkers have argued that everything that begins to exist must have a cause, and therefore the universe must have a cause, leading to an infinite regress or requiring an uncaused cause. The multiverse concept provides a scientific framework for an uncaused cause. If the multiverse itself is eternal and timeless, then it doesn't begin to exist. It simply exists necessarily and forever. Individual universes within it, like our own, do begin to exist, and they have causes rooted in the laws of the multiverse, a quantum fluctuation, a bubble nucleation, a branching event. But the larger whole requires no cause because it never came into being. The pre-temporal state is no longer a mysterious, singular void that existed before our universe. It is the eternal, foundational ground of all being, the infinite and timeless canvas upon which countless temporal stories are written. It makes the pre-temporal not an anomaly to be explained, but a natural and inevitable feature of a reality far grander and more magnificent than we ever imagined. But this powerful, universal experience of time's one-way direction, the feeling that moments flow from past to future and never the other way, is perhaps the most significant clue we have that our temporal reality emerged from something deeper. This relentless forward march, known as the arrow of time, finds its most robust scientific explanation not in gravity or quantum mechanics, but in the seemingly mundane world of thermodynamics, specifically in a concept called entropy. Entropy is essentially a measure of disorder or randomness within a system. The second law of thermodynamics states that in any isolated system, the total entropy can never decrease. It can only stay the same or increase over time. This isn't just a suggestion, it's a fundamental statistical inevitability. It's why your coffee cools down in the room instead of the room heating up from your coffee, why a shattered glass never spontaneously reassembles itself, and why we remember the past but not the future. The increase of entropy provides a powerful, objective direction to time's arrow in our universe, yet this law presents us with a profound cosmic puzzle. If entropy always increases, then to have the universe we see today, a state of relatively low entropy with structured galaxies, stars, and planets, it must have started in a state of even lower entropy. The Big Bang appears to have been a moment of extraordinarily low disorder, an immensely ordered and finely tuned configuration that has been unraveling and becoming more disordered ever since. This is known as the past hypothesis, the idea that the initial low entropy state of the universe is a mysterious boundary condition, a fundamental fact about our cosmos that itself requires an explanation. It's the ultimate example of getting something for nothing. We have this vast, complex universe evolving from a state of incredible simplicity and order, and we don't fully understand why that initial state was so special. This is where our journey into the pre-temporal realm offers a breathtaking solution. In a state beyond time, the very concept of entropy may be undefined or constant. Without a sequence of events, there can be no increase or decrease in disorder. The pre-temporal universe, whether we imagine it as a quantum foam, a mathematical landscape, or a holographic data surface, would exist in a state of perfect equilibrium or timeless potential. The arrow of time wouldn't just be absent, the concept would be meaningless. The transition from this state to our own temporal universe, then, is not just the beginning of time, but the very imposition of a temporal direction. The Big Bang becomes the moment this timeless equilibrium was broken, setting the cosmic pendulum of entropy swinging in one irrevocable direction and launching the universe on its long, slow journey from order towards disorder. Some theorists propose that this low entropy boundary condition wasn't a random accident, but was actually sculpted by the pre-temporal state itself. Imagine the timeless realm not as a void, but as a landscape of all possible initial conditions for a universe. The vast majority of these possible starting points would be high-entropy states, cosmic chaos, hot and dense in a completely random, disordered way. A universe born from such a state would be instantly filled with maximum entropy, leaving no room for the formation of structure, stars, or life. It would be a thermodynamic dead end. Our universe, with its inexplicably low initial entropy, is a spectacular outlier. Its beginning was incredibly specific and ordered. This suggests that the pre-temporal realm somehow selected for or enabled this specific low-entropy configuration, perhaps through a process of quantum tunneling that favored the most probable path from timelessness to time, a path that began with a clean, simple, and orderly slate. This provides a stunningly elegant thermodynamic basis for the origin of everything. The emergence of time is inextricably linked to the breaking of symmetry in entropy. From a timeless state of balanced potential, our universe crystallized with a built-in gradient, a slope from order to disorder that time itself must slide down. The past hypothesis is no longer a standalone mystery, but a direct consequence of the universe's origin in a pre-temporal state. The arrow of time is not a fundamental feature of reality, but an emergent property, a story that began with the first moment and will continue until the last star burns out and the universe reaches its final, quiet state of maximum entropy. Our relentless experience of moving forward is the living, breathing consequence of that singular, ancient event, a permanent reminder that our cosmos was born from a realm where such direction had no meaning at all. Now, if the universe truly emerged from a timeless state of pure information and mathematical potential, we have to ask a truly fascinating question: how could such a system possibly maintain its stability and function without the familiar crutch of time to organize cause and effect? This is where we can venture beyond traditional physics and borrow a powerful idea from an entirely different field: cybernetics. Cybernetics is the study of self-regulating systems, how they use feedback loops to maintain stability and achieve goals. It's the science behind your home's thermostat, which constantly measures the temperature and switches the heating on or off to maintain a set point. It's the principle behind your body's ability to regulate its own temperature, or a company's ability to adjust its strategy based on market feedback. These are all processes that happen in time. But what if we apply this concept of self-regulation to a reality where time is not fundamental? What if the pre-temporal cosmos wasn't a chaotic void, but a supremely balanced, self-correcting system that achieved perfect homeostasis without ever needing a single clock tick to do so? Imagine the universe not as a thing that evolves, but as a timeless, static structure that is inherently self-referential. In a conventional control system, a sensor measures an output, compares it to a desired set point, and sends a signal back to an actuator to make a correction. This feedback loop requires the time it takes to measure, compare, and act. But in a timeless reality, this entire process would have to be collapsed into a single, simultaneous relationship. Think of it not as a loop, but as a perfectly balanced equation or a perfectly woven tapestry where every thread is already in the right place, holding every other thread in place. The goal of the system, perhaps its stability, or its ability to give rise to a temporal universe like ours, isn't achieved through a sequence of actions, but is encoded directly into its fundamental, timeless architecture. The universe is its own set point, eternally self-maintaining because its very structure is the definition of balance. We can find hints of this in the bizarre world of quantum mechanics, specifically in the phenomenon of quantum entanglement. When two particles become entangled, their properties are linked in such a way that measuring one instantly determines the state of the other, no matter the distance between them. This connection seems to operate outside of our everyday notions of cause and effect. It doesn't require a signal to travel through space in time to create the correlation. It's as if the correlation is just a fundamental, timeless fact about the relationship between those two particles. Now scale this idea up to a cosmic level. Perhaps the pre-temporal state was a vast, timeless network of quantum correlations, a cosmic web of instantaneous feedback links where every part knew about every other part simultaneously. This network wouldn't need to process information over time because all the information is mutually defined and self-referential from the outset. It's a system that is perfectly controlled because it was never out of control to begin with. Its stability is its very essence. This cybernetic perspective offers a radically new way to think about the origin of our temporal universe. The Big Bang transition might not have been a random quantum fluctuation or a spontaneous tunneling event. Instead, it could have been a controlled release of potential, a transition that was inherently built into the stability of the timeless system itself. Picture a dam holding back a vast reservoir. The dam is a stable, homeostatic structure, but it also contains a carefully engineered spillway. When the water level rises past a certain point, the spillway activates, releasing water in a controlled manner to prevent the dam from breaking. The timeless cosmos could be analogous to that dam, a perfectly balanced, self-regulating structure. The accumulation of a certain kind of potential, perhaps a quantum potential, could have triggered a built-in cosmic spillway, the Big Bang, which released that potential in the controlled, orderly explosion that became our expanding universe. The low entropy, the specific physical constants, the very laws of physics themselves might not be accidents, but the predetermined output of this timeless control system, ensuring the resulting universe would be stable and capable of supporting complexity. This is, of course, a highly speculative but profoundly inspiring idea. It draws from cybernetics, quantum physics, and systems theory to paint a picture of cosmic origins that is less like a random explosion and more like the flawless execution of a timeless, preordained plan, not by a designer, but by the inherent, self-regulating logic of reality itself. It suggests that the universe we inhabit is not a chaotic accident, but the intended outcome of a deeper, eternal balance. This interdisciplinary approach doesn't replace the other theories we've explored. It complements them, adding a new layer of understanding that focuses on function, purpose, and stability. It enriches our toolkit, allowing us to imagine the pre-temporal realm not as an empty stage or a formless void, but as the most sophisticated and perfectly balanced control system imaginable, one whose ultimate output was the gift of time itself. This brings us to one of the most profound and controversial intersections of science and philosophy, the role of the conscious mind itself. If time is not a fundamental stage but an emergent property, a compelling and deeply unsettling question arises. Could consciousness be the very mechanism that conjures the experience of time into being? Is the flowing present we all feel not a feature of the external world, but a creation of the internal observer? This idea pushes us to consider that mind and cosmos might not be separate entities, one observing the other, but are instead codependent, arising together from a timeless ground of pure potential. To explore this, we must venture into the world of quantum mechanics, where the act of observation has puzzled scientists for a century. In the famous double-slit experiment, particles like electrons behave as probability waves when not observed, seeming to pass through both slits simultaneously and creating an interference pattern. But the moment a measuring device is placed to determine which slit the electron goes through, this wave-like behavior collapses. the electron acts like a single particle and the interference pattern vanishes. The standard interpretation, known as the Copenhagen interpretation, states that the wave function which describes all possible states of a particle collapses into a single, definite reality only upon measurement or observation. But this immediately raises a thorny question. What exactly constitutes an observer? Is it a machine, or does it require a conscious mind to finally actualize reality from a cloud of possibility? This is where the mathematician and physicist Roger Penrose enters the conversation with a truly extraordinary hypothesis. Penrose, collaborating with anesthesiologist Stuart Hameroff, proposed that consciousness is not a simple byproduct of brain chemistry, but a fundamental feature of the universe, rooted in the very fabric of reality at the quantum level. Their theory, called orchestrated objective reduction, suggests that within the neurons of our brains are structures called microtubules. These tiny components are so small that they can operate by the rules of quantum mechanics. Penrose argues that a quantum superposition, a state of multiple possibilities, can exist in these microtubules until it reaches a certain threshold of complexity, at which point it collapses due to its own gravitational weight. This collapse is not triggered by an external observer. It is the moment of conscious experience. Each collapse is a discrete quantum blip of awareness, and the rapid sequence of these blips creates our seamless illusion of a flowing stream of consciousness, and by extension, the flow of time itself. This theory offers a breathtakingly elegant, if speculative, bridge between the timeless quantum world and our temporal experience. In this view, the pre-temporal cosmos of quantum potential doesn't require a divine observer to kickstart it. Instead, consciousness and cosmos emerge together. The timeless quantum field is a sea of unactualized possibilities. The arising of consciousness, through the specific physical process Penrose and Hameroff describe, is what performs the continuous act of observation that collapses these possibilities into a sequential, ordered reality. Time doesn't flow, consciousness flickers, and from that rapid flicker, the flow is constructed. We are not just inhabitants of time, we are the very instruments that play its melody, drawing a linear experience from a nonlinear source. This perspective finds a powerful echo in a school of philosophy known as idealism. Unlike materialism, which holds that matter is fundamental and mind is a product of it, idealism flips the script. It proposes that consciousness is the primary, fundamental reality, and the physical world is a manifestation of it. The great idealist philosophers, from George Berkeley to Immanuel Kant, argued that we can never know the thing in itself, we only know our perceptions of it. Modern thinkers like Bernardo Kastrup have updated this framework for the quantum age, suggesting that the seemingly external world is actually a representation within a universal, timeless consciousness. The Big Bang, in this view, is not the beginning of matter, but the moment this universal consciousness began to dream a stable, shared reality into existence, complete with the laws of physics and the dimension of time to give that dream structure and sequence. So what does this mean for our pre-temporal universe? It suggests that the realm beyond time is not a cold, mathematical void, but a state of pure, undifferentiated consciousness, a potentiality of mind waiting to know itself. The transition to a temporal universe is the moment this consciousness turns inward, initiating a process of self-observation. Each act of observation, from the first quantum fluctuation to the gaze of a human astronomer, is a thread weaving the tapestry of time from the timeless loom of mind. This is not to say the universe doesn't exist without us, but that existence and observation are two sides of the same coin. The cosmos exists as a potential, and consciousness is the agency that actualizes it into the story we call history. This idea challenges the very core of the scientific method, which seeks an objective reality independent of the observer, and instead proposes a deeply participatory universe where mind and matter are inextricably linked, dancing together from a timeless origin into the fleeting, beautiful experience of the present moment. For centuries, long before physicists ever wrote a single equation about quantum gravity, artists and writers have been using their own tools, paint, words, metaphor, and melody, to probe the very same mystery of a reality beyond time. They haven't been building telescopes or particle colliders. They've been building windows into the human soul, and through those windows we catch profound glimpses of the timeless. This creative exploration isn't a lesser or fanciful counterpart to scientific inquiry. It is a parallel and deeply intuitive journey toward the same truth, offering a visceral, emotional understanding that complements the abstract beauty of a mathematical model. When we look at a painting by Salvador Dali or lose ourselves in the verses of T.S. Eliot, we are not just observing art, we are engaging in a form of quantum philosophy, feeling the instability of time in our bones long before our minds can fully grasp the equations that describe it. Consider one of the most iconic images in all of modern art, Salvador Dali's The Persistence of Memory, with its limp, melting clocks draped over a barren landscape. This isn't just a surrealist fantasy, it is a powerful psychological and metaphysical statement. Those soft watches are a direct assault on our assumption that time is a rigid, reliable ruler of our lives. Dali is showing us time as it might exist in a dream state, or perhaps as it truly is at a fundamental level, fluid, relative, and ultimately an illusion. The ants crawling on the one solid clock in the painting suggest decay, that even the mechanical measurement of time is subject to entropy and corruption. The painting doesn't explain the Wheeler-DeWitt equation, but it makes you feel its implications. It creates a palpable sense of temporal vertigo, a visual representation of a universe where clocks don't dictate reality, but instead sag under the weight of a deeper, more mysterious truth. Literature offers an equally rich tapestry of temporal exploration. T.S. Eliot's monumental poem Four Quartets is essentially a deep, meditative dive into the nature of time and eternity. Eliot distinguishes between chronological time, the linear, sequential time of our daily lives that he calls here, there, and everywhere, and a different kind of timeless moment, a point of intersection where the eternal breaks into the temporal. He writes of the still point of the turning world, a concept that feels remarkably similar to the frozen, block universe of physics or the singular, timeless instant of a quantum state before collapse. For Eliot, this still point is not a void but a place of profound meaning and liberation from the relentless flux. His poetry doesn't seek to solve time but to transcend it through a spiritual and artistic consciousness, suggesting that the only way to truly grasp eternity is not through calculation, but through a moment of heightened awareness, what he might call a moment of grace. This theme of cyclical time, which we see in modern cosmology's bouncing universes and eternal inflation, is perhaps the oldest story humanity has ever told. From the ancient Hindu cycles of creation and destruction, the Kalpas, to the Norse myth of Ragnarok and the rebirth of the world, cultures have repeatedly envisioned time not as a straight line but as a great circle. James Joyce's Finnegan's Wake is a towering, dizzying monument to this idea. The novel, famously beginning in the middle of a sentence and ending by looping back to its own beginning, is designed as a vast cycle. Its language is a dreamlike collage of puns and portmanteaus from dozens of tongues, collapsing all of history and myth into a single, swirling, eternal now. Reading it is a deeply disorienting experience. deliberately mirroring the confusion one might feel when trying to conceive of a universe with no start and no finish, where everything is simultaneously present. Joyce wasn't a physicist, but he was a poet of consciousness, and he built a literary model of a cyclic cosmos long before it became a mainstream scientific hypothesis. Even in popular culture, these ideas persist and shape our collective imagination. The concept of a timeless, eternal recurrence is the central horror and fascination of Friedrich Nietzsche's philosophical novel, Thus Spoke Zarathustra, with the idea that we are doomed to live our lives over and over again, exactly the same for all eternity. This thought experiment forces a radical evaluation of how we live in the present moment. In film, Christopher Nolan's Interstellar uses the power of cinema to make a five-dimensional, timeless reality visually comprehensible. The protagonist, Cooper, doesn't just travel through time. He moves into a realm where time is a physical dimension he can navigate and manipulate, represented as a breathtaking tesseract of bookshelves containing every moment of his daughter's life. It's a Hollywood blockbuster attempting to visualize what a physicist might call a Cauchy surface or a space-time manifold, making the abstract tangibly emotional for a global audience. This enduring artistic quest tells us something fundamental about the human condition. Our science seeks to understand the universe through external observation and measurement, but our art seeks to understand it through internal experience and expression. They are two different languages describing the same indescribable thing. The artist's studio and the physicist's laboratory are both workshops where the nature of reality is being probed, one with a brush and the other with equations, but both with a profound sense of wonder and a shared frustration with the limits of ordinary perception. This cultural lens doesn't provide proof for a pre-temporal universe, but it provides something equally valuable: meaning. It connects the cold, abstract majesty of cosmic origins to the warm, beating heart of human fear, hope, and curiosity. It reminds us that the drive to peek behind the curtain of time is not a mere technical puzzle, but a core part of what makes us human, an endeavor that has always required not just mathematics, but metaphor, not just data, but dreams. But if the block universe is real, if every event from the dawn of time to the distant future is eternally fixed within the four-dimensional fabric of space-time, then we are forced to confront one of the most unsettling questions imaginable. What happens to our concept of morality in such a cosmos? If every choice we believe we make was already written into the structure of reality billions of years ago, can we truly be held responsible for our actions? This isn't just an abstract puzzle for philosophers. It strikes at the very heart of our justice systems, our personal relationships, and our deepest sense of self. The idea of a timeless universe doesn't just rewrite physics. It threatens to unravel the entire ethical framework of human civilization. This dilemma is rooted in a philosophical position known as determinism. In a block universe, the future is just as real and unchangeable as the past. This suggests that the chain of cause and effect is absolute and predetermined. Every thought in your brain, every decision you make, from what you'll have for breakfast tomorrow to the most profound moral choice of your life, is simply the inevitable result of the prior state of the universe, all the way back to the initial conditions of the Big Bang. In this view, you are always going to make those choices. The feeling of weighing options is an illusion, a story your brain tells itself as it marches along a single, predetermined track. This is the classic challenge to free will. If we are nothing more than complex biological machines playing out a script written by the laws of physics, then praise and blame, reward and punishment seem to lose all meaning. How can we punish a murderer for an act they were always destined to commit? How can we reward a hero for an act of bravery they never truly chose to perform? Yet, many philosophers and scientists argue that this grim conclusion is a misinterpretation, a failure of our language and intuition to keep up with the science. They propose a more nuanced view called compatibilism. Compatibilists agree that the universe is deterministic at a physical level, but they argue that this doesn't negate free will, it simply redefines it. Free will, in this view, isn't about being an uncaused cause, magically operating outside the laws of nature. Instead, it's about acting in accordance with your own desires, beliefs, and character without external coercion. Imagine a cup of coffee cooling on a table. Its temperature change is determined by the laws of thermodynamics. Now imagine you choose to drink that coffee because you're tired and you want caffeine. Your choice was also determined by your desire for caffeine, your belief that coffee will help, and your internal brain states. But the key difference is that the coffee cup had no say in the matter, while your action was an expression of your own internal will, even if that will itself is a product of prior causes. From this perspective, you still have free will because your actions flow from you. The fact that you are the product of a deterministic universe doesn't make your choices any less yours. This compatibilist view allows us to preserve a robust sense of moral responsibility. We hold people accountable not because they could have magically done otherwise in an absolute sense, but because their actions reflect their character. Punishment and reward aren't about retroactively changing a fixed past. They are tools we use within the timeline to shape future behavior and reinforce social norms. Sentencing a criminal is a causal event that changes their environment and the environment of others, influencing future actions that are just as fixed within the block. Our legal and ethical systems become part of the deterministic tapestry, not contradictions to it. They are the mechanisms by which society, as a complex system, self-regulates and maintains order along its predetermined path. The block universe model might even deepen our sense of compassion and empathy. If every person's life is a completed story with their struggles, triumphs, and suffering eternally embedded in reality, it can foster a profound sense that every moment matters. The pain of a victim and the remorse of a perpetrator are not fleeting illusions. They are permanent, unchanging features of the cosmic landscape. This could lend a new weight to our actions, a sense that what we do is not just for the transient present, but is forever inscribed into the history of the universe. It encourages us to think carefully about the kind of eternal marks we want to leave on the space-time continuum. Do we want our chapter to be one of kindness, generosity, and justice, or one of cruelty and indifference? Even in a determined world, our choices, or the experience of making them, define the quality of that eternal reality. Ultimately, the ethics of a timeless cosmos don't provide easy answers, but they force a radical expansion of our perspective. They challenge us to disentangle our intuitive, time-bound notion of free will from a more sophisticated understanding of what it means to be a conscious agent in a causally closed universe. It suggests that morality might not be about bucking the system of cause and effect, but about understanding our role within it and striving to be the kind of causal force that creates a more just, beautiful, and compassionate world. A world whose story, though already complete, is one we can still feel proud to be a part of. Strange as it may seem, some of the most powerful tools for understanding the timeless origins of our cosmos aren't found in billion-dollar particle colliders or deep space telescopes, but in the devices we use every day. The very technology that keeps us connected and entertained holds within it profound metaphors for a reality without time, offering us a new language to grasp these abstract cosmic ideas. Think of a modern computer processor. At its heart is a clock, a crystal oscillator that ticks billions of times a second, synchronizing every calculation, every memory access, every operation in a strict, relentless sequence. This is how we experience the world, one moment after another, a linear procession of cause and effect. But now, imagine a computer without a clock. This isn't science fiction. It's an actual design called asynchronous computing. In such a system, operations don't wait for a global timer. Instead, each component activates only when the data it needs is ready, sending a signal to the next component to begin its work. The entire system functions through local handshakes, not a central drumbeat. The processing gets done, order emerges, and a result is produced, but there is no single, overarching timeline governing the process. The system operates in a state of distributed, relational coordination that is strikingly similar to how physicists describe a pre-temporal quantum realm, where events are defined by their correlations to each other rather than their position on a universal clock. This idea scales up dramatically when we consider the architecture of artificial neural networks, the engines behind modern AI. When a deep learning model is trained on a massive dataset, say millions of cat photos, it doesn't learn in a sequential, step-by-step manner like a human studying a textbook. The network processes the entire dataset in parallel, adjusting the millions of weights between its artificial neurons all at once. There is no first lesson and last lesson. The knowledge of what a cat looks like emerges holistically from the simultaneous adjustment of countless connections. The final trained network is a static structure, a frozen, timeless map of relationships between data points. When you then give it a new picture, it doesn't think through the problem in a temporal sequence. It simply activates this frozen web of correlations all at once to produce an answer. This is a powerful analogy for the block universe theory. The entire four-dimensional cosmos could be seen as a kind of static, trained neural network, a vast web of events where every moment is eternally connected to every other. Our experience of moving through time is like feeding the present moment as an input into this frozen network and receiving the next moment as an output, creating the illusion of a flowing present from a structure that is fundamentally timeless. These technological metaphors form the basis of a fascinating and controversial scientific paradigm known as digital physics or the computational universe hypothesis. Pioneered by thinkers like Konrad Zuse, Edward Fredkin, and Stephen Wolfram, this theory proposes that the universe is fundamentally not a physical thing, but an informational process. At the very bottom level of reality, there aren't tiny, vibrating strings or loops of energy, there are bits. The universe is a gigantic, ongoing computation. Space and time are not the stage on which this computation happens. They are themselves the products of the computation. In this view, the pre-temporal state is the ultimate source code, the algorithm, the program, the set of initial rules that begins running. The Big Bang is the moment the cosmic computer was powered on and the first calculation began. What we perceive as the flow of time is simply the sequential processing of this cosmic program, one Planck-length step after another. The most radical version of this idea is the concept of a cellular automaton, a simple grid of cells that follow basic rules based on the states of their neighbors. The most famous example is John Conway's Game of Life. From a few simple initial conditions and a handful of rules, astonishingly complex patterns emerge, grow, interact, and die out, all from a timeless set of instructions. There is no time inside the simulation. The time is just the iteration count, the step number of the calculation being run on the computer outside the simulation. Digital physics turns this idea inside out, suggesting that we are inside the cellular automaton. Our reality is the complex pattern emerging from the relentless application of simple, pre-temporal rules to the cosmic grid. The laws of physics are the algorithms, particles, forces, and even the sensation of time itself are the output. This provides a stunningly elegant framework for a timeless origin. The universe didn't begin in time, it began with a rule set. The mystery of the first cause is transformed into the mystery of the first line of code, shifting the question from physics to mathematics and logic. These technological metaphors don't prove that the universe is a computer, but they give us a desperately needed vocabulary to describe how something as ordered and complex as our reality could possibly emerge from a state where the very idea of sequence has no meaning. So where do we go from here, after such a mind-expanding journey through timeless realms and cosmic origins? It's natural to wonder if any of these breathtaking ideas can ever move beyond beautiful speculation and into the realm of testable science. The answer is a resounding yes, and the path forward is being forged right now in a thrilling convergence of theoretical brilliance, cutting-edge technology, and ambitious new experiments. The future of timeless cosmology isn't just about more elegant equations. It's about building the tools to finally listen to the whispers of the pre-temporal universe itself. One of the most exciting frontiers is the emergence of quantum computing as a cosmic simulator. Imagine trying to understand the formation of a hurricane by building a miniature storm in a laboratory tank. That's precisely what quantum computers promise to do for the birth of the cosmos. These extraordinary machines operate on the same quantum principles that govern the universe's first moments: superposition, entanglement, and probability. Researchers are now beginning to program these computers to simulate the conditions of the very early universe, effectively creating a tiny, digital model of a pre-temporal state. They can tweak parameters, run the simulation forward, and watch how a structured spacetime might emerge from a timeless quantum foam. This isn't just a theoretical exercise, it's a virtual laboratory where we can test the predictions of loop quantum gravity, string theory, and other models against each other, searching for which one produces a universe that looks like our own. It's like having a time machine made of qubits, allowing us to run the tape of creation over and over again to see how it might truly unfold. But we're not just relying on digital recreations. We are also building ever more powerful instruments to directly observe the faintest echoes of the beginning. The Event Horizon Telescope, which gave us the first unforgettable image of a black hole's shadow, is a stunning example of this. By linking radio telescopes across the globe to create an Earth-sized virtual dish, the EHT doesn't just study black holes, it probes the extreme limits of gravity and spacetime. Future iterations of this project, perhaps with telescopes in space, could be sensitive enough to detect the subtle imprints of a pre-Big Bang phase. For instance, if our universe is the result of a cosmic bounce, the specific way spacetime was stretched and compressed during that event could have left a unique fingerprint on the polarization of light at the very edge of the observable universe. The EHT and similar instruments are essentially tuning in to a cosmic radio station, and we are just now learning how to listen for the oldest songs on the dial. Looking further ahead, a new generation of space-based observatories is poised to open windows into the first fleeting instance after the Big Bang. The Laser Interferometer Space Antenna, or LISA, is a planned mission that will consist of 3 spacecraft flying in a giant triangle, millions of kilometers apart and connected by laser beams. This incredible observatory will be dedicated to detecting low-frequency gravitational waves, the ripples in spacetime caused by the most cataclysmic events, like the merging of supermassive black holes. But it might also hear something far more profound. the faint primordial hum of gravitational waves generated directly by the Big Bang itself, or even by the quantum fluctuations of the pre-temporal vacuum. Detecting this background rumble would be like finding the cosmic equivalent of a fossilized dinosaur bone, a direct relic from a time before time. The specific frequency and pattern of these waves would be a smoking gun, potentially allowing us to distinguish between a one-time inflationary beginning and a cyclical bounce from a previous era. This incredible journey from math to measurement is fueled by an unprecedented collaboration across disciplines. Theoretical physicists are refining their models to make specific, testable predictions. Cosmologists and astronomers are designing the experiments to go out and gather the crucial data. And perhaps most importantly, a new breed of data scientists and machine learning experts is developing the algorithms to sift through the unimaginably vast datasets these projects will produce, searching for the subtle signals that would be invisible to the human eye. It's a global human endeavor, a testament to our species' insatiable curiosity and our relentless drive to understand our place in the cosmos. The ultimate goal is to move these magnificent ideas from the blackboard to the benchmark of reality. We want to be able to look at a set of data from a quantum computer simulation, from a gravitational wave observatory, or from the cosmic microwave background, and say with confidence, this is how the universe began. The journey into the pre-temporal realm is no longer a solitary philosophical quest. It is a hard-nosed scientific expedition, and we are all fortunate enough to be living at the moment when the first maps are being drawn. The answers won't come easily, but the very act of seeking them is expanding the boundaries of human knowledge in ways we are only just beginning to imagine. Now, with all these mind-bending theories about a cosmos beyond time, it's completely natural to hit a wall of skepticism. Our brains, wired for a world of cause and effect, often recoil at these ideas, simplifying them into misconceptions that can sound like pure magic or metaphysical nonsense. One of the biggest and most understandable misunderstandings is the idea that a pre-temporal universe must be a vast, empty void, a literal nothingness where absolutely nothing exists. This is perhaps the most common stumbling block because we instinctively picture before as a period of waiting, an inactive stage before the actors arrive. But this is where our language and our intuition betray us. The pre-temporal state isn't a void of nothingness. It's a realm of pure potential, a different kind of something that operates by rules we're only beginning to grasp. Think of it not as an empty theater, but as the entire script, the cast list, the stage directions, and the musical score all existing simultaneously before the curtain ever rises. The stuff of reality is all there, but it hasn't yet been organized into the play we recognize as space-time. It's a domain of quantum possibilities, mathematical relationships, and informational structures, all very real and active, just not in a way that involves sequential time. This leads directly to another major misconception, that these ideas are untestable and therefore fall outside the realm of real science, landing squarely in the domain of philosophy or even religion. It's a fair criticism after all. How can you run an experiment on something that, by definition, has no time for experiments to occur within? The beauty of modern cosmology is that it found a way. Scientists don't need a time machine to visit the pre-temporal state. They can look for its fingerprints all over our present universe. The cosmic microwave background radiation is like a baby picture of the cosmos, and encoded in its subtle temperature variations could be the telltale signs of a pre-Big Bang phase, like the specific patterns that would be left by a quantum bounce or the imprint of a parent universe. Furthermore, the quest for a theory of quantum gravity is itself a testing ground. If a theory like loop quantum gravity or string theory can successfully unify the laws of physics and accurately predict phenomena we can observe, like the behavior of particles in accelerators or the nature of gravitational waves, then its description of the pre-temporal state gains tremendous credibility. It's not about observing the unobservable directly. It's about finding a complete and consistent mathematical framework that explains everything we can see, and that framework inevitably points to a reality beyond time. Another pervasive myth is that a timeless origin implies a single, one-time creation event, which then inevitably leads to the question of what caused that event, pushing us toward a divine creator or an unsatisfying infinite regress. But most of these scientific models completely sidestep this issue. In the eternal inflation multiverse, for example, there is no first universe and no first cause. The meta-reality that spawns bubble universes is eternal and necessarily existent. It doesn't have a beginning, so it doesn't need a cause. Our Big Bang was just a local event within this eternal landscape, a single bud on an infinite, timeless tree. Similarly, the no-boundary proposal eliminates the need for a beginning altogether by describing a cosmos that is finite yet without any singular edge or starting point. These aren't clever word games. They are rigorous mathematical solutions that show how our universe could be self-contained and self-originating, requiring no external prime mover. The science isn't arguing for or against a creator. It is simply demonstrating that a creator is not a scientific necessity to explain the origin of our specific universe. Perhaps the most subtle misconception is that if the past is fixed in a block universe, then the future must also be fixed, robbing us of all free will and making our lives meaningless. This is a profound philosophical concern, but it conflates two different levels of description. Physics describes the universe from a God's eye view, the entire timeline as a single, static object. But our human experience is from within the timeline. Our consciousness, our reasoning, our deliberations, and our choices are all real processes that are part of that fixed block. The fact that the entire story is written doesn't change the fact that we are the characters living it, making decisions that feel real and have real consequences within the narrative. Your choice to have coffee this morning was always going to happen, but your process of wanting coffee and deciding to brew it was an essential part of that eternal story. The block universe doesn't negate your experience, it contains it. Dispelling these myths is crucial because it allows us to engage with these revolutionary ideas on their own terms, not through the fog of our own cognitive biases. It lets us appreciate the sheer intellectual bravery of the scientists who are piecing this puzzle together, using the powerful tools of mathematics and observation to explore the ultimate frontier of reality itself. So what does this all mean for you and me, right here, right now, sitting in our seemingly ordinary lives governed by clocks and deadlines? It's one thing to grapple with the physics of a timeless cosmos, but it's another entirely to feel its implications in the quiet moments of our own existence. If the block universe is real, if every moment of our lives from our first breath to our last is eternally fixed in the cosmic structure, then the frantic anxiety that often defines modern life begins to feel strangely out of place. The pressure to constantly achieve, to race against the clock, to mourn the past or fear the future, can start to soften when viewed through this grander lens. It doesn't promote laziness or apathy, rather, it can foster a profound sense of being. Your life isn't a fleeting spark in the dark that will be extinguished and forgotten. It is a permanent, indelible thread woven into the eternal tapestry of reality. Every moment of joy, every act of kindness, every struggle you've overcome, they are not lost to the past. They are forever part of the universe's story, as real and enduring as the stars themselves. This perspective can be an incredible source of comfort, transforming our relationship with time from one of lack and scarcity to one of abundance and permanence. This shift can also invite a deeper sense of wonder into our daily routines. The simple act of looking up at the night sky takes on a new dimension. You're not just looking at points of light millions of years in the past. You are gazing at a single, frozen moment in a four-dimensional cosmos, a moment that includes the light's journey, your act of seeing it, and everything in between. That evening cup of coffee, the warmth of the sun on your skin, the sound of a loved one's laughter, these aren't just transient experiences rushing by on a conveyor belt. In a very real sense, they are eternal. They have always existed and will always exist in the space-time block. This isn't just a philosophical thought experiment. It's a practice in mindfulness that can root us more deeply in the present. When we truly internalize that this moment is not just passing but is a permanent fixture of reality, we might be more inclined to fully inhabit it, to savor it, and to treat it with the reverence it deserves. For many, this connection to the timeless is most powerfully accessed not through equations, but through practices that quiet the mind's constant chatter about past and future. Meditation, for instance, is essentially the practice of touching the timeless. In deep states of mindfulness, the incessant narrative of the ego, the regrets and plans that tie us to the linear flow of time, can momentarily fall away. What remains is a pure, undifferentiated awareness of the present, a state that many describe as feeling expansive, peaceful, and eternal. This is not so different from the physicist's description of a pre-temporal state of pure potential. In those moments, we aren't thinking about timelessness. We are, in a small way, experiencing it. Similarly, the feeling of awe we get from witnessing a breathtaking natural landscape or getting lost in a piece of profound music can momentarily suspend our sense of self and time, connecting us to something much larger and more permanent than our individual stories. Ultimately, the most beautiful gift this idea offers might be a renewed sense of perspective on our own challenges and triumphs. The argument you had yesterday, the project you're stressed about at work, the personal goal you're straining to achieve, while immensely important from within your timeline, they are also just one small part of an immense and magnificent whole. This isn't to diminish our struggles, but to contextualize them within a cosmos of unimaginable scale and beauty. Understanding that we are part of a reality that transcends time can inspire a more holistic, compassionate, and patient worldview. It encourages us to see the bigger picture, to be kinder to ourselves and others, and to find meaning not just in the destination, but in every single step of the journey, knowing that each step is a forever part of the cosmic dance. This fascinating divergence in how cultures perceive time isn't just a matter of historical curiosity. It reveals two profoundly different ways of being in the world, and both offer invaluable insights for our modern quest to understand a pre-temporal cosmos. Western thought, heavily influenced by Judeo-Christian theology and later by the scientific revolution, overwhelmingly embraces a linear model of time. Imagine time as a single, straight arrow shot from a bow. It has a definitive beginning, a creation event, like the moment God said, "Let there be light," and it flies forward through history toward a final destination, an ultimate culmination like the Christian concept of the Second Coming or a scientific heat death. This perspective imbues time with a sense of purpose and progression. History is a story moving from a point of origin toward a specific end goal, and our individual lives are chapters within that grand narrative. This linear view is the bedrock of much of Western science and historiography, fueling our desire to find a definitive starting point for the universe, a first cause that set the entire cosmic story in motion. It's the driving force behind the search for the Big Bang singularity. Now journey eastward and you encounter a completely different temporal landscape. In traditions like Hinduism and Buddhism, time is most often envisioned as a great turning wheel, vast, cyclic, and without a true beginning or end. The cosmos undergoes endless cycles of creation, preservation, and dissolution, known as kalpas in Hinduism. These cycles can span billions of years, but they are just seasons in an eternal process. There is no absolute start date. There is only the endless, rhythmic pulse of the universe breathing in and out. This view is even more pronounced in Buddhism, which directly challenges the very reality of a permanent self existing in time. The fundamental teaching of impermanence, or anicca, states that all conditioned things are in a constant state of flux. The feeling of a continuous, enduring self is considered an illusion. In this framework, clinging to a linear timeline of our lives is a source of suffering. Liberation comes from realizing the timeless, unchanging nature of awareness itself, which exists prior to the world of form and time. This is strikingly similar to the quantum physicist's view of a timeless wave function from which our temporal reality emerges. Taoism, the ancient Chinese philosophy, adds another layer to this Eastern view. It emphasizes harmony with the Tao, which is the ultimate, undefinable reality that is the source of everything. The Tao is often described as being eternal and beyond time, a concept echoed in the opening lines of the Tao Te Ching. The Tao that can be told is not the eternal Tao. Time and change are seen as part of the natural flow of this eternal principle, expressed through the dynamic interplay of yin and yang. Rather than a linear arrow, time is more like a flowing river or the changing seasons, a natural process to be aligned with, not a resource to be managed or a path to a distant finish line. The goal is not to progress through time but to find a timeless wisdom within it, to become like the uncarved block, simple and at peace with the eternal present. When we place these ancient cultural frameworks alongside modern cosmology, the parallels are nothing short of astonishing. The Western linear drive finds its ultimate expression in the relentless scientific pursuit of a theory of everything, a single set of equations that can trace the universe back to a definitive T=0. The Eastern cyclic view finds a powerful echo in scientific models like the oscillating universe of loop quantum cosmology or the eternal inflation of the multiverse, where our Big Bang is not a unique beginning but one event in an infinite series. The Buddhist concept of the illusion of the self finds a strange counterpart in the block universe theory, where our feeling of moving through time is a cognitive construct, a narrative we impose on a reality where all moments equally exist. And the Taoist idea of a timeless, underlying principle that is the source of all form resonates deeply with the mathematical universe hypothesis, which suggests the cosmos is built on an eternal foundation of mathematical truth. This beautiful convergence suggests that the human quest to understand time and origins is a universal one, expressed through different languages: the language of myth, the language of philosophy, and the language of mathematics. They are not competing truths but complementary perspectives, each offering a unique lens on the same profound mystery. The Western mind seeks to measure the arrow's flight and trace its trajectory, while the Eastern mind seeks to understand the archer and the target. One perspective gives us the powerful, analytical tools of science to probe the mechanics of the cosmos, while the other offers a wisdom that can help us live with the breathtaking implications of what we discover. Together, they form a more complete picture of our relationship with time, reminding us that the greatest mysteries often require not just one way of knowing, but many. To grasp how physicists can even begin to describe a reality without time, we must venture into the rarefied world of advanced mathematics, where the conventional rules of geometry and algebra are reshaped into powerful new tools. These aren't just abstract playthings for theorists, they are the essential scaffolding required to build a model of a pre-temporal cosmos. At the heart of this endeavor is a fundamental shift in perspective, moving from a universe of things happening in time to a universe of eternal relationships. Imagine the difference between trying to describe a dance by listing the position of each dancer at every second, a temporal description, versus describing the intricate patterns and connections between the dancers that define the dance itself, regardless of when it is performed. This relational view is the key that mathematics provides, allowing us to model a cosmos where when is irrelevant and only how things are connected matters. One of the most profound frameworks for this is category theory. Often called the mathematics of mathematics, category theory doesn't care about the internal specifics of objects. It focuses exclusively on the relationships or morphisms between them. Think of it as the ultimate study of networks and connections. For example, in a simple category, the objects could be cities like New York, London, and Tokyo. The morphisms wouldn't be the cities themselves, but the flight paths connecting them. The category theory perspective is concerned with how you can get from one city to another, the possible routes, and how those journeys compose. You can fly from New York to London, and then from London to Tokyo, and that composition is itself a new morphism from New York to Tokyo. Now apply this to the cosmos. The objects could be quantum events or states of the universe. The morphisms are the possible transitions or relationships between them. Crucially, time is not a pre-existing stage. The ordering of events emerges purely from the web of these relational pathways. The entire history of the universe can be described as a vast category, a frozen, timeless network where every event is eternally connected to every other, and the illusion of sequence is just a path we choose to follow through this eternal web of connections. Another revolutionary mathematical tool is non-commutative geometry, developed by the mathematician Elaine Connes. Standard geometry relies on commutative algebra, where the order of operations doesn't matter. 3 times 4 is the same as 4 times 3. This commutative property is deeply tied to our experience of a smooth, continuous space where you can measure positions. But what if space itself is not smooth? What if, at the tiniest possible scale, at the Planck length, spacetime is fuzzy and granular, like a digital photograph that appears smooth from afar but is actually made of discrete pixels? Non-commutative geometry provides the language for this. In this framework, the coordinates of a point do not commute. This means measuring position in one direction, and then another might give a different result than measuring in the reverse order. This fundamental fuzziness implies that the very concept of a point in space, and by extension a point in spacetime, breaks down. You can't have a singularity, a point of infinite density, because points themselves are no longer well defined. This mathematics naturally describes a reality that is fundamentally granular and relational, not made of distinct things in a container, but of interacting relationships where the very notion of a location is derived, not primary. It paints a picture of a pre-temporal state not as a void, but as a vibrant, interacting network of non-commutative relationships from which the familiar dimensions of space and time later crystallize. The power of these tools is magnified immeasurably when they are wielded to understand symmetry. In physics, symmetry isn't just about beauty, it is the deepest principle governing the laws of the universe. The forces between particles, the conservation of energy, the very fact that the laws of physics are the same everywhere, all of these are expressions of underlying symmetries. Groups like SU3 and SU2 are not just abstract symbols, They are the mathematical DNA that dictates how particles like quarks and electrons can interact and transform into one another. These symmetry groups are timeless. The relationship described by SU3 doesn't change, it simply is. This allows physicists to describe the potential for all possible interactions in the universe without ever invoking a timeline. The pre-temporal state can be envisioned as a realm of pure, unbroken symmetry, a perfect frozen state of all potential. The emergence of our temporal universe, then, is the story of symmetry breaking, a phase transition where this perfect symmetry is fractured, giving rise to the distinct forces, particles, and the arrow of time we experience. The mathematics of group theory provides the map for this transition, showing how a timeless, symmetrical potential can give birth to a rich, complex, and temporal world. Ultimately, these mathematical frameworks, category theory, non-commutative geometry, and group theory, are more than just calculation tools. They are a new form of perception, a way of seeing reality that transcends our innate, time-bound intuition. They reveal that the cosmos might be fundamentally relational, a vast and intricate structure where everything is defined not by what it is in isolation, but by its connections to everything else. This relational universe is static and complete, a cosmic monolith that contains every moment, every event, and every possibility in one timeless whole. Our journey from past to future is not a voyage through this structure, but a path within it, a reading of an eternal story. The elegance of this mathematical vision is its breathtaking economy. It does not require a mysterious first cause or a creator outside the system. The universe is a self-contained, self-explaining mathematical structure, and our quest to understand it is the journey of a part of that structure slowly becoming aware of its own magnificent, timeless form. Now consider the remarkable technology of quantum computing, a field that operates on principles feeling almost custom-made for exploring these very ideas. While our classical computers rely on a strict, sequential order of operations governed by a central clock, quantum computers dance to a completely different rhythm. Their fundamental unit, the qubit, defies our everyday logic. Unlike a standard bit that must be a definitive 1 or a 0, a qubit can exist in a state of superposition, representing both 1 and 0 simultaneously. It's not that it's undecided, it genuinely holds both potential outcomes at once until the moment it is measured. This isn't just a faster way of processing, it's a different way of being. The qubit's reality is a cloud of probability, a timeless coexistence of multiple states, echoing the pre-temporal quantum realm where all possibilities simply exist without a need for chronological order. This parallel deepens dramatically when we introduce the phenomenon of quantum entanglement, what Einstein famously called spooky action at a distance. When two qubits become entangled, they form an intimate connection that transcends space and, crucially, time. Measuring the state of one qubit instantly determines the state of the other, no matter how far apart they are. There's no signal traveling between them, no communication that takes time. Their fates are linked in a way that suggests their correlation is a primary, timeless fact of their relationship, not a secondary effect that needs to propagate. This is a stunningly concrete example of how the quantum world operates on a principle of immediate correlation rather than causal sequence. It provides a working, man-made model for how a universe might function without relying on a linear timeline, where relationships are fundamental and the illusion of time emerges from how we interact with the system. Researchers are now harnessing this unique power of quantum computers to do something extraordinary, simulate the very conditions of the early universe. Think of it as creating a miniature, digital universe in a lab. Classical computers struggle with this task because modeling the quantum behavior of an entire cosmos requires tracking an impossible number of variables evolving simultaneously. But a quantum computer, with its inherent ability to process a multitude of states at once, is perfectly suited for the job. Scientists can program qubits to represent the quantum fields present at the birth of the cosmos, set the initial conditions based on a specific theory, like loop quantum gravity or string theory, and then let the quantum processor run. It doesn't calculate step by step. It allows the quantum system to evolve the simulation holistically, exploring all possible histories at once to find the most probable outcomes. This allows us to effectively run the tape of the Big Bang or a Big Bounce over and over again with different parameters, watching to see which models produce a universe that looks like our own. This isn't just theoretical play. Teams at institutions like Google and IBM are already running small-scale simulations of holographic principles or quantum tunneling events that could have sparked cosmic inflation. By observing how these simulated universes evolve, or more accurately, how their quantum states correlate, physicists can look for verifiable signatures. For instance, a simulation based on a bouncing universe model might predict a specific pattern of primordial gravitational waves, while an inflationary model predicts another. These simulated fingerprints can then be compared against real-world data from telescopes like the James Webb or future gravitational wave observatories. A quantum computer becomes a bridge, a practical tool that takes the abstract mathematics of timeless cosmologies and turns it into testable, virtual experiments, bringing us closer than ever to understanding how our flowing reality emerged from a state of timeless potential. Trying to picture a universe without time is like trying to imagine a color you have never seen. It forces us to use metaphors and analogies that can only hint at the profound strangeness of such a state. If we could somehow step outside our own timeline and perceive this pre-temporal reality, what would actually meet our gaze? It wouldn't be a black, empty void, nor would it be a chaotic storm of flashing lights. Instead, the closest visual analogy might be that of an impossibly intricate, frozen sculpture. A four-dimensional crystal where every event, every particle, every moment of joy and sorrow is held in a single, eternal, and perfectly detailed embrace. This cosmic monument wouldn't be carved from stone, but from the relationships between things, a vast web of mathematical and geometric connections where every point is simultaneously connected to every other point, not through distance in space, but through pure correlation and meaning. Think of a magnificent tapestry, but one woven in more than 3 dimensions. From our limited perspective within the tapestry, we see only the individual threads we are currently passing over, the present moment. But from this outside, God's eye view, the entire design is visible at once. The Big Bang isn't a starting knot, it's simply one particularly dense and complex cluster of weaving. The formation of our solar system, the rise and fall of civilizations, and the distant heat death of the universe are all equally present, their patterns forever fixed in the fabric. There is no fading of the threads with age. The vibrancy of the moment you were born is just as bright and real as the moment you are experiencing right now. This isn't a static picture of death, but a state of complete and total existence where nothing is lost and everything simply is forever. The beauty of this vision is not in movement, but in perfect, unchanging completeness, a kind of cosmic immortality where every beautiful moment is preserved for eternity. Yet to call it entirely frozen might be a misleading oversimplification. Another way to envision it is as a dynamic but timeless dance. Imagine every single particle, every force field, every ripple of gravity as a dancer. In our temporal universe, we see the dance unfold step by step, a sequence of movements leading from a beginning to an end. But from the pre-temporal perspective, the entire dance is known in its totality. The dancers aren't moving through time, they are frozen in every possible position of their routine simultaneously. The beauty lies in the choreography itself, the perfect, eternal relationships between the dancers' positions. You could study the complex pattern of where a dancer's hand is in relation to another's foot at any point in the routine, and that relationship is a permanent, unchanging fact. The dance doesn't happen, it is a structured, beautiful whole whose elegance is defined by these countless frozen correlations. This shifts the aesthetic from one of narrative and sequence to one of geometry and pattern, where the value is in the intricate, interconnected design of the whole. This concept has been intuitively explored by artists for centuries, often evoking a deep, emotional response that precedes intellectual understanding. The composer Olivier Messiaen, for instance, sought to escape what he called the tyranny of the bar line by creating music based on complex rhythmic patterns and ancient Greek and Hindu rhythmic cycles, rather than a simple, pulsing meter. Listening to his works like the Quartet for the End of Time, you can feel a sense of time dissolving, replaced by a soaring, ecstatic state that feels both immense and suspended. Similarly, the visual artist M.C. Escher mastered the art of depicting impossible, timeless geometries, waterfalls that flow in perpetual motion yet never progress, staircases that ascend endlessly yet lead nowhere. His art doesn't move, yet it creates a powerful cognitive feeling of an infinite, unchanging process, a loop that exists entirely outside of linear time, captivating our minds precisely because it defies our everyday experience of sequence and conclusion. Engaging with these artworks gives us a visceral, emotional taste of the timeless, a feeling that is both bewildering and profoundly beautiful, connecting us to the sublime mystery that modern physics is now trying to map with equations. But if time itself is not a fundamental feature of reality, but something that emerges from a deeper, timeless layer, we are immediately confronted with one of the most powerful objections to the entire idea. How can we possibly explain the undeniable reality of change? Our world is defined by motion and process. Planets orbit, seasons turn, plants grow, and we ourselves age. Everything is in a state of flux. This seems to be the most obvious proof that time is real and flowing. To suggest that time is an illusion feels like denying the very evidence of our senses. Yet, this paradox might actually hold the key to a far more profound understanding of reality, one where change is not a product of time but its very source. This radical reversal of perspective is at the heart of a theory known as relationalism, a philosophy of time with roots stretching back to the great thinkers Gottfried Leibniz and Ernst Mach. They argued that time does not exist as an independent entity, a kind of invisible river that carries all events along with it. Instead, they proposed that time is a derivative concept. It emerges from the simple, undeniable fact that things change relative to one another. Think about it this way: we never experience time directly. We never feel 5 minutes passing in the abstract. What we actually experience is change. We see the hands of a clock move from one number to the next. We feel the sun's warmth increase as it rises higher in the sky. We notice the battery icon on our phone depleting. Time is the concept we invent to measure and quantify that change. In the relational view, change is the primary, fundamental reality. Time is just the story we tell about it, a convenient numerical index we use to order and compare different rates of change. This idea becomes crystal clear when we examine the most basic tool for measuring time, the clock. What does a clock actually do? It doesn't measure some mystical substance called time. A clock is simply a device that performs a very specific, regular type of motion, and allows us to compare other, less regular motions to it. An ancient sundial compares the motion of a shadow to the apparent motion of the sun across the sky. A grandfather clock compares the swinging of a pendulum to the gradual descent of its weight. An atomic clock, the most precise timekeeper we have, compares everything to the mesmerizingly consistent vibrational frequency of a cesium atom. In every single case, the clock is measuring motion against motion, change against change. The second, our standard unit of time, is literally defined by the International System of Units as the duration of 9,192,631,770 periods of the radiation corresponding to the transition between two hyperfine levels of the ground state of the cesium-133 atom. It's a mouthful, but it's a definition based entirely on a specific, observable change in the physical world. Time is the number we read out from this process of comparison. This means that in a truly timeless block universe, change doesn't disappear. It is simply reconceived. Instead of a single, evolving world, we have a vast, static network of events, each event containing within it a record of its relationship to all other events. The dynamism we perceive is our conscious journey through this frozen landscape, a journey where we are only aware of one event, one slice of the block at a time. Our memory provides the record of prior events, and our anticipation provides a prediction of future ones, creating the powerful and convincing illusion of a flowing present. The change is real, it's the progression that is the illusion. The entire cosmic movie exists on the real, complete, but we experience it one frame at a time. This resolves the paradox beautifully. Change and motion are not proof of a fundamental time. They are the raw materials from which our brains construct the experience of time. A timeless reality is not a frozen, lifeless statue. It is a four-dimensional sculpture of unimaginable complexity, where every conceivable motion and transformation is captured and preserved for eternity, waiting for a conscious observer to trace its contours and call it history. While physicists use complex equations to model a pre-temporal cosmos, some of the most compelling explorations of timelessness happen not in academic journals, but in the stories we tell each other at the movies or in the pages of our favorite books. Popular culture has long been fascinated with the idea of stepping outside of time, and these creative portrayals serve as a crucial bridge, translating abstract scientific concepts into emotional, visceral experiences that resonate with millions. They are the public's first and often most memorable introduction to these mind-bending ideas, shaping our collective imagination about what might be possible. A film like Christopher Nolan's Interstellar doesn't just entertain, it functions as a massive public physics lesson, using the power of cinema to make five-dimensional reality feel tangible. When the protagonist Cooper plunges into the black hole Gargantua, he doesn't find a destructive singularity but a vast, multi-dimensional tesseract, a labyrinth of bookshelves representing every moment in his daughter Murph's life. He can push on books to create gravity anomalies, literally reaching across time to communicate. This is a stunningly creative visualization of the block universe theory. The tesseract isn't a place in time, it's a library of time, a structure where every moment exists simultaneously and can be navigated spatially. Nolan consulted closely with physicist Kip Thorne to ensure the black hole's appearance was scientifically accurate, but the tesseract is a work of inspired speculation that captures the feeling of a timeless reality far more effectively than any textbook diagram ever could. It translates the cold mathematics of four-dimensional spacetime into a deeply human story of love and connection, making the abstract profoundly personal. Yet for every scientifically grounded depiction, there are many more that take creative liberties, often simplifying or sensationalizing the concepts for dramatic effect. The beloved classic A Wrinkle in Time by Madeleine L'Engle introduces the idea of a tesseract as a way to fold the fabric of space and time, allowing for instantaneous travel across the universe. While the term is borrowed from geometry, L'Engle's use of it is more fantasy than physics. In the story, tessering is a thrilling, sometimes dangerous journey through a supernatural medium. This captures the wonder of the concept, the idea that the vast distances of space might be overcome by manipulating the geometry of reality, but it glosses over the immense energies and bizarre spacetime curvature that such an feat would actually require according to general relativity. This isn't a criticism of the story, it's a recognition of its genre. The book uses the language of science as a springboard into a magical adventure, inspiring awe and curiosity in young readers that might later lead them to explore the real science. These portrayals are less about accuracy and more about planting a seed of wonder, using the poetic idea of wrinkling time to open minds to the possibility that our universe is far stranger than it appears. Some of the most common misrepresentations arise from the need to provide a simple, visual metaphor for audiences. Time travel stories, in particular, often treat time as a linear path that can be walked backward or forward, like a hallway with doors to different years. This reinforces the intuitive but flawed idea of time as a single, universal river flowing in one direction. In reality, most physical models of time travel based on general relativity, like traversable wormholes or closed time-like curves, involve bending the entire four-dimensional spacetime continuum into a loop. You wouldn't travel back in a straight line. You would take a shortcut through a higher dimension, arriving back at a point in your own past light cone. The difference is subtle but crucial. One is like rewinding a tape, the other is like folding the tape so that two separate points touch. The former suggests the past is a place you can visit and change, potentially creating paradoxes, while the latter often implies a self-consistent, predetermined timeline that was always looped, a concept much more in line with the block universe view. By analyzing these common tropes, we can use them as teachable moments to clarify the real physics and separate Hollywood excitement from theoretical possibility. Ultimately, the value of these pop culture explorations isn't measured by their scientific precision, but by their ability to engage the public in a conversation about the fundamental nature of reality. They provide a shared cultural vocabulary, a set of images and ideas, that makes these daunting topics approachable. When someone watches Doctor Who and hears the Doctor explain that time is a big ball of wibbly-wobbly, timey-wimey stuff, they are being introduced to the concept of nonlinear time in a fun, memorable way. When they watch the ancient time loops in Arrival, where learning an alien language literally rewires a linguist's brain to perceive time non-sequentially, they are experiencing a powerful metaphor for how consciousness and reality might be intertwined. These stories make the philosophical implications of timelessness immediate and emotional. They allow us to grapple with questions of fate, free will, and identity in a context that feels safe and entertaining, long before we dive into the mathematics of the Wheeler-DeWitt equation. They are the gateway drug to cosmology, sparking the curiosity that drives a viewer to seek out a documentary or a video like this one, eager to learn what's real, what's speculative, and what remains one of the greatest mysteries of our existence. And so our journey through the timeless brings us back to ourselves, to the very heart of what it means to be a conscious being in a cosmos of such staggering depth and mystery. We have ventured from the quantum foam to the string theory landscape, from the philosophical implications of a block universe to the psychological construction of our own temporal experience. What becomes undeniably clear is that this quest is far more than an academic exercise in theoretical physics. It is a profound exploration that reverberates through every layer of our existence, challenging the stories we tell ourselves about reality, identity, and our own significance. The idea of a pre-temporal cosmos does not diminish our place in the universe. Instead, it elevates it, embedding our fleeting lives within an eternal, magnificent structure where every moment of awareness, every act of love, and every spark of curiosity is forever inscribed into the fundamental fabric of all that is. This perspective invites a quiet but powerful shift from seeing ourselves as transient passengers on a rushing river of time to recognizing ourselves as integral threads in a timeless, cosmic tapestry. As we close this exploration, I want to extend a heartfelt thank you for embarking on this intellectual adventure. The mysteries of the cosmos are vast and often humbling, but they are best confronted with a shared sense of wonder and a collaborative spirit. Your curiosity is what fuels this entire endeavor. The conversation does not end here. I am genuinely eager to hear which of these theories resonated most deeply with you. Did the bouncing universe of loop quantum cosmology capture your imagination? Or did the holographic principle's vision of a projected reality feel more compelling? Perhaps the philosophical questions about free will in a block universe left you with more questions than answers. Share your thoughts, your doubts, and your own speculations in the comments below. This is our digital agora, a place to gather and collectively puzzle over the greatest questions ever asked. If this journey into the pre-temporal has sparked a hunger for more, you are not alone. This is just one of many deep dives into the enigmas that surround us. We have so many more frontiers to explore together. The nature of black holes, the search for consciousness in the universe, the ongoing puzzle of dark matter and dark energy. To ensure you don't miss out on these upcoming adventures, make sure to subscribe to the channel and hit that notification bell. It is the best way to continue this journey of discovery alongside a community of fellow wanderers. Finally, carry this sense of awe with you. The next time you glance at a clock, remember that the time it measures may be a beautiful, persistent illusion. The next time you look up at the night sky, consider that you are not looking into a deep past, but across an eternal present. Let that feeling of connection to the timeless deepen your experience of the now, enriching your appreciation for this single, breathtaking moment of awareness we all share. Never stop questioning, never stop exploring, and above all, never